So at this point we take a kind of turn from thermodynamics into statistical mechanics. Before I talk much about statistical mechanics, I just want to do a kind of preliminary check. Who's familiar, for some fairly relaxed value, familiar with classical mechanics done on phase space? Anyone not familiar with them? Okay, so I can just kind of help myself to classical phase space and get on with it. Okay, that's fine. If I turn out to overestimate what counts as familiar here at any point, then shout, and I'll do a kind of micro tutorial on anything I'm assuming, but I'm not going to be using a lot. Okay, so the kind of starting issue in statistical mechanics, let me start this off from the perspective of thermodynamics, is something like this. The systems that we're interested in studying, among other things, via equilibrium thermodynamics, have also got mechanical descriptions, or at least we've got fairly good reason to think they have mechanical descriptions. Now, the real mechanical descriptions are quantum mechanical. There is a widespread tendency in foundation statistical mechanics to assume that it's safe just to use the classical mechanical framework. I think for a lot of reasons, in a lot of situations, that's not actually a safe move and should be made very cautiously. But I think for the sake of anything I'm going to say in the next couple of hours, I can get away with doing everything classically. So just to avoid getting embroiled in the quantum measurement problem, I'm going to do that. So we're operating on the kind of fiction systems we're interested in are mechanical systems, that is to say, they're described within the framework of classical mechanics. They're described by, their states are described by some point in some phase space that's got finitely many dimensions, and for simplicity we might as well pretend is the phase space of n-point particles, in which case it's got 6 n dimensions, 3 positions and 3 momenta for every particle. And we've got a Hamiltonian function, and the dynamics of the system we're studying are given by Hamilton's equations as applied to that Hamiltonian. Okay, so how does all of that fit into anything we might call statistical mechanics? So far that just sounds like ordinary mechanics. There's a kind of narrative that runs through a lot of the way this is discussed in the foundations of philosophy of statistical mechanics that's worth dwelling on a moment. And I think the narrative goes something like this. Statistical mechanics is basically a foundational project for thermodynamics. In particular, the job of equilibrium statistical mechanics is to recover for us the various principles that govern the behaviour of thermodynamic systems at equilibrium as we bring them into contact and manipulate them in various ways. And the task of non-equilibrium statistical mechanics is to tell us how it is that systems that initially begin at equilibrium head to equilibrium. So very crudely, the task of non-equilibrium statistical mechanics is to underpin the minus first law. The task of equilibrium statistical mechanics is to underpin the rest. Okay, that picture of statistical mechanics, I think, is basically wrong in a fairly systematic and fabricated sense. It's not that an aspect of that task is not a relevant part of statistical mechanics. It's not that there isn't an important foundational project within statistical mechanics which underpins thermodynamics. But thinking of statistical mechanics itself as a foundational project fails to do justice to how the subject actually works. And getting that across and getting across how the subject in fact works, and what it does get used for, is one of the main things I want to do across the next couple of hours. To pause briefly though, here's a sociological reason why it should be fairly clear to us that statistical mechanics is not a predominantly foundational project. Think for a moment what the general attitude is within physics to foundational work. The answer is normally something between overt hostility at worst and a kind of cautious tolerance for a small amount of it around the edges at best. Then think about just how much statistical mechanics is done in physics departments, and you realise that whatever those guys are mostly doing, it can't be foundations. Okay, so let's ask what they are doing. And here's a way of getting it that goes back to thermodynamics. And I want, for the minute, to talk, and probably for the next hour or so, to talk mostly about equilibrium statistical mechanics. I think my clause here talks about this being the logic of non-equilibrium statistical mechanics, so I'll defend that by either saying part of the logic of non-equilibrium statistical mechanics requires equilibrium statistical mechanics as a setup, or to say that you should regard equilibrium statistical mechanics as the limit of non-equilibrium statistical mechanics as you approach equilibrium. I'm not being serious for that last suggestion. All right, think about equilibrium statistical mechanics and think about thermodynamics as we've seen it. Suppose that you know of some physical system or collection of physical systems, only that they are governed by the principles of thermodynamics. And suppose you finessed your way around the various concerns that Jos has been raising about just what those principles are, and whether we really have an unconstructive way of characterizing them. Just for the minute, suppose we've got some rough grip on what the principles of thermodynamics are, we've got a bunch of systems, we know that they're governed by the principles of thermodynamics, and we want to know what can we predict about those systems on the basis of that knowledge alone. And the answer, I think, is precious little. We can say some very general things. We know that they'll approach an equilibrium state. And we know the equilibrium state is characterized, modulo certain concerns, basically by the system's energy and the external constraints that affect it. I mean, the shape of the box, for instance, and the energy it has. We know that these things have some state functions called temperature. We know they have some state functions called entropy. And we know something very abstract about the relations between those state functions and what happens when systems move into an out-of-thermal contact. That's pressure, that's basically it. If we've got a box that we're told is a gas at equilibrium, merely from thermodynamics we don't know so much as to whether pushing a knot or pulling on it is a way to get work out of it. If we've got a system that is confined to the left-hand half of a box by a partition, and all we know about the system is that it satisfies the principles of thermodynamics, we don't have a clue what happens when we take the partition away. Just to make that clear, suppose that the system consists of a block of rock confined, in quotes, to the left-hand side of the box by a partition. It is not a principle of thermodynamics that when you whip out the partition, the rock equilibrates across the box. So how do we get somewhere with thermodynamics? Well, we kind of saw this tacitly with Wayne's presentation yesterday. Pretty soon, in order to do much work with thermodynamics in detail, you start introducing particular systems. And the canonical classic one introduced in physics textbooks is the ideal gas. And what do we know about that system? Well, jumping happily to the end of our account of how statistical mechanics works and just helping ourselves to all of those concepts of entropy and the like that we obtained with so much labour within thermodynamics understood primitively, the equation of state for something like an ideal gas can be understood as somehow telling us the parameters of the system in terms of the other parameters. And just to labour that a little bit, we have the equation of the ideal gas having something like the following form. This is one of the various ways we can write it. Small ball, isn't it? So in that form, I've got the entropy of the gas as a function of the volume of the gas V and the energy of the gas U. And I'm using U where K equals 1 here.
And those are logs, right?
Those are logs, yes. Sorry, Lun is log, yeah.
Right. The second kind of looks like an H.
No, sorry. Let me give it again in this. I will write to Moquette. I have longer than I realised, so I can take my time writing. Okay, when I don't know an equation of state for a thermodynamic system, I know very, very little. When I know an equation of state, I know a lot. Even the fact that the equation of state is just a function of the volume and the energy has already told me a lot. It's told me that the box is a fluid. It's told me that the thermodynamic state of the box at equilibrium depends on the size of the box. It doesn't depend on the shape of the box. If the box is kind of curvy or twisted in various ways, that's not supposed to matter. So that's already some information there. The quantitative form of this thing gives me a lot more information. If I differentiate, and if I compare that equation to the first law of thermodynamics in its differential form, which you remember is for a system with just this one parameter, which so can be rewritten as you can assume that any algebraic mistake I make in this is deliberate and is there as a test for students. So that's a command. If I compare that expression for the ideal gas with that expression in general, I can basically read off the relation between temperature and energy. 1 over T is NCV over U, so temperature is proportional to energy. I can read off the value of pressure, P over T is N over V. That gets me out the ideal gas law in my casually units set to something manageable way. I get out the structure of the ideal gas, I get out its behaviour from its equation of state. Both explicitly through calculations of that kind and tacitly just by knowing what the equation of state depends on.
Did you use the ideal gas law as an independent ingredient here?
I don't think so.
Nope. How did you get temperature?
I think I have ds equals, comparing the two expressions, I can read off 1 over T is mcv over u, and P over T is N over V. And I've lost the ideal gas constant into some casualness about coefficients.
This may be a stupid question, but where did the log U come from, the expression of entropy? I can see where the log V comes from, but is there a simple way to motivate, without going through the full story, why it's log U?
From the point of view of thermodynamics qua phenomenological thermodynamics, from the point of view of having nothing known other than that, nothing at all, I've given you this equation of state stipulatively.
Okay.
You shouldn't, if you think you know where the log V is coming from, you're already assuming too much.
Okay, good.
Yeah.
Yeah, just wondering, just check, this isn't necessarily sort of unique to thermodynamics, in the sense that, like, I don't know, when we're doing general mechanics, I also, as we've just told you, like, F equals MA,
Right.
and so it's now just like,
Gives you virtually nothing, yeah.
right,
Right.
fitting in the
Yeah, or in Hamiltonian dynamics, if I tell you there is a Hamiltonian, it's a function of P and Q, and Hamilton's equations follow, then likewise, I've told you some very general facts about the system without supplementing it with a lot more I haven't told you much. So no, that's dead right. Okay, so where do equations of state come from? And where do we get the knowledge of what the coordinates of the dependent equation of state depend on? As far as thermodynamics itself is concerned, as Neil brings up, it's just something you add to the theory. Thermodynamics you can think of it as a machinery. Given a system characterized by an equation of state, you can get out various concrete thermodynamic claims about that system, but the equations of state themselves are just phenomenology of the theory. And thermodynamics by itself doesn't tell you that any of the properties of the system beyond those that go into thermodynamic calculations. So from the equation of state, I've got out the pressure, I've got out the temperature. If I'm interested, for instance, in the question about whether an ideal gas fills the box uniformly, or am I interested in something like what's the distribution of velocities in the particles within an ideal gas, the latter I'm not going to be able to get at at all through thermodynamics. The former I might be able to tease my way towards in some way that relies on suggesting the extent to which maybe this equation implies some kind of extensivity, but in general even things like that are not going to be given to me direct. So I've got two questions on which thermodynamics is silent. What's the equation of state? What are the properties of the system at equilibrium beyond those characterized by the equation of state? Equilibrium thermodynamics is basically the game of answering those questions. The task that we're mostly engaged in doing in equilibrium thermodynamics is one, working out equations of state from the microphysics, and two, working out the other properties of systems of equilibrium from the microphysics.
I think you meant equilibrium statistical mechanics.
What did I say?
Thermodynamics.
Yes, thank you. Yeah. Equilibrium statistical mechanics involved in those tasks. Equilibrium statistical mechanics is mostly about calculating the state functions and the other properties of the systems. What I want to do next is say how it does it. Now, I use the word how rather carefully. I'm not going to say why it does it. I'm not going to say how the methods of statistical mechanics work. I'm not going to say what their justifications are. I just want to lay out what they actually are. So I want to show here what we actually are in the business of doing when we do equilibrium statistical mechanics. It's our job, our philosophers, to understand what the right foundation of that task is, But just as we're not going to get somewhere with the foundations of thermodynamics before we have at least a rough and ready picture of what thermodynamics is, so if we want to understand the foundations of statistical mechanics regarded as a project in itself, rather than as itself just a foundational project, we better be moderately clear about what equilibrium statistical mechanics is actually doing, how it actually works, what the bits of machinery are that it relies on. Okay. So, Wayne mentioned that virtually everyone who takes a course on statistical mechanics, I'm certainly in this category, is confused by it and struggles to follow it. Explanations of the principles of statistical mechanics are kind of dotted with various, well, this is why this is justified and motivated, this is why this is reasonable, here's the kind of sort of reason why we do things this way. It's all very unsatisfactory and very confusing and makes it hard to see what's going on. I'm not going to give you any motivation at all, I'm just going to tell you the black magic that's going on in equilibrium thermodynamics. Remind those of you who've done the course how it works. Then we can start thinking why it works. But let's be clear what it is to start with. I'm going to break it into two pieces. I'm going to fill in that over the course of the next few minutes, so this board's going to sit there as a kind of background object. Here's the starting point of the situation we're going to think of. We've got a classical mechanical system. The system's characterized by its Hamiltonian, and to characterize the kind of situations we're interested in statistical mechanics for thermodynamic purposes, we assume that the system's Hamiltonian is itself dependent on a bunch of parameters. So if we're interested in a system that's confined to a box, for instance, the Hamiltonian of the system is going to have some parameters in it that track the shape of the box. And if you want to imagine modelling this, then you probably model the box by some potential that's flat, except towards the edge of the box, and then it goes up very sharply without limit. So I'm starting with my phase space. Parameter-dependent Hamiltonian. So this is a function, yeah? It's a function on the phase space. The job of the function is to tell us the dynamics, but which function I have in mind depends on some parameters. This is those of you who've seen this kind of math, this is a functional dependence of the Hamiltonian function on the parameters. And again, the case to keep in mind whenever I get abstract here is just the box of gas. The parameters there are just, let's say, the length and breadth and height of the box. So think of the box is rectangular, the parameters track its length and its breadth and its height, and the particular Hamiltonian is going to be a kinetic energy term for each of the particles, plus a potential energy term whose job it is to keep the particles in the box, and basically to leave them alone as long as they keep away from the limits of the box. Okay, now think about the phase space of this whole system, yeah? This is some very high dimensional space. If I've got a box of gas, say, well, it needn't be high dimensional, but if I'm dealing with a big macroscopic system, it's likely to be very high dimensional. So I've got, say, 10 to the power of 20 gas molecules, then the phase space has 6 times 10 to the power of 20 dimensions. H is a function on that space. I can consider those surfaces in the phase space of constant H. And I can define the volume of those surfaces. In fact, I can define the volume of those surfaces very easily. It's 0. The volume of any surface in a higher dimensional space is always 0. So what we mean by the volume of the surface is what we normally mean in these contexts. We imagine that it's got some very small width, delta U, and we say that its volume times delta, its quote volume times delta U is just the real volume of that sort of slice of thickness delta U. And I'm going to call, just following the standard statistical mechanical terminology, the density of states for a particular value of the energy of the system and of the parameters, because remember, change the parameters will change the shape of the hypersurfaces. The density of states is just the phase space volume of that surface. So just to make it explicit, there are various ways of turning that into an epsilon delta framework and making it a completely sharp mathematical statement. Anybody who's sufficiently worried about those kind of things to want to know how it's done is also sufficiently mathematically switched on to be able to do it themselves, so I leave those necessary. I'm going to pause there and just ask you, if anyone is not sure what's going on here, I don't mean conceptually what we're doing with it, I just mean what the thing is I've just defined. This is the right moment to ask, because I'm going to use a lot of this stuff. So take a moment to think about that, see if you've got it. Haven't say so.
Can I just,
yeah.
I don't know if I don't understand or if I just can't see. The volume dependent on u and the parameters and the 1 to n. And
yeah.
What does it say? Does that just say equals delta u or what?
It is.
Yeah.
That's just times.
Okay.
So the problem is because I've got this has to be, if you like, a volume density, because I'm considering it for u, and a given surface has 0 volume. So the density of states times a really thin shift in energy equals the volume of all the points in a shell which has that energy to within that very thin amount. I mean, I'll just do a quick kind of very crude sketch of the kind of thing we're thinking of. So if you imagine this is the single particle, maybe a harmonic oscillator or something. Here's the phase space. There's going to be the surface of constant energy for, say, a harmonic oscillator for this little corner of phase space is just going to be curves like this. So if this is equal, this is the curve energy u. I've got some little strip here with delta u. And so for this system, the density of states would be the volume of this little thin shell here divided by delta u. And of course, actually, this goes on for negative q and negative p. And then the fact that I've got dependence on the parameters is saying, well, one thing I could do is consider this at a different energy, so look at a different hypersurface, and look at how that changes the volume. And another thing I could do is just take that hypersurface and consider the same hypersurface as I modify the parameters and so shift the Hamiltonian. So if, say, I change the springiness of the spring in a harmonic oscillator, this surface might move out that way or move in that way.
If you take the volume of that region and divide it by delta u, would it be permitted to call the result the area of that?
I think there is I don't think it is, because there's a dependency on the gradient of u. So if I have a faster or slower dependency of u away from the hypersurface, then I mean, of course it's going to be proportional to the ordinary gradient, but there's going to be a proportionality term, and the proportionality term might vary across different bits of the hypersurface. Yeah.
Just check the various lambdas are just like single numbers rather than functions, or
in my current treatment, yes. Nothing at least so far prevents it being a functional dependence, but that's just starting to get a bit too tricksy.
Is this thing something the V? It's something called the structure function?
I don't know. Sorry.
Yeah.
Yes.
Yeah.
The two structure functions, right? This is the structure function.
Structure function is one of these terms in physics that I think is kind of overloaded in computer science terms. It also gets used for various features of nuclear scattering.
And sometimes it's, oh my god.
Yeah.
Oh, okay.
Yeah, I just made up curly V. This isn't necessarily a standard terminology. By the way, just to flag that we can do all this stuff quantum mechanically, I won't systematically tell you the quantum versions of all this, but I'll tell you at this point, the quantum version of this is that the density of states, you can think of it as discretized because quantum energy levels for a finite and controlled system are going to be discrete, and you can think that the density of states for a particular energy is just the dimension of the Hilbert space, of the eigenspace of that given energy within the Hilbert space. And again, that could shift as I move the parameters around. But normally we'd be dealing with quantum mechanical systems big enough that I consider some little width of energy delta U that covered a great many energy levels, and so effectively you go to something continuous for the density of states even in quantum theory.
Sorry, using the lambdas are parameters that the Hamiltonian has that are, you mentioned, related to the box, size of the box.
Yeah.
What could be also, of course, other things.
Whatever you like, yeah. At the moment, I've been awfully abstract. I mean, for instance, if I go back to the one-particle oscillator, then the Hamiltonian I could think about as H. I can think of that as a Hamiltonian that's dependent on one parameter. So as I shift omega, if I think that's a parameter in my control or whatever, I'm shifting the Hamiltonian system. It wouldn't be terribly hard to write down explicitly a workable form of the Hamiltonian for particles in a box, but I don't think it'll slow us down unnecessarily. Okay, who cares? Answer, it gives us our first step of our recipe. So the density of states is a function of the energy in the parameters. Take its logarithm, that gives you another function of the density in parameters. Declare, without justification, never apologize, never explain, that is the state function. The thing on the left-hand side is the entropy. Why is that true? The level of presentation I'm doing here, who knows? Let me just let's just play that out, just a kind of quick reminder of how fast and powerful this kind of technology is. So let's take our particle in the box, okay? I've got n particles, let's assume they interact with each other, basically not at all. So what's the energy of that collection of particles? Well, the potential energy of each of the particles is basically naught, because we're assuming that basically none of them are going to be in the high potential region where we're bouncing off, and we're assuming they don't interact. And so the energy of all of the particles is the sum of the kinetic energies of all of the particles divided by the mass of the particles. So for that system, I think of the system as characterized by the positions q1 through qn of all the particles and the velocities p1 through pn of all the particles. I've got u P1, Qn, P1, Pn basically equal to, very nearly to these vectors. Okay, and so if I now ask, what's the phase space?
The Hamiltonian, right? So,
there's a reason I hedged by putting a slight caution here. That's what my parameter.
Is U a different function than H?
U is going to be very nearly the same function as H for energy, for configurations that are not in the potential region at the very edge of the box that's keeping things in. That's the only reason I hedged.
I see.
I mean, to regard this as exactly the Hamiltonian, I have to be allowing that my phase space, my theory is a kind of limit point rather than a literal version of this story, because in the way I've got this set up, the volume is entering tacitly into the framework by just a straight constraint upon the possible values of the positions of the particles rather than directly dynamically. You see what I mean? If the phase space is just given by where all the particles are, there's a whole bunch of configurations that have insanely high energies because they're 6 feet through the wall of the box or something, and I define the walls of the box as some ridiculously high potential. Okay, so with that caution in place, if you want to ask what's the phase space volume available to these n particles if I know their total energy is some energy u. So we don't care where they are. So if you think about how to put the phase space together, I can factorize the phase space into the position bit of the phase space and the velocity bit of the phase space. The position bit of the phase space, other than the limitation that we're in the box, doesn't matter at all. So the term in the density of states I get from the position of the phase space is just for each particle the volume of the box. So the position term in the whole thing is the volume of the box to the power of the number of particles. Which is be explicit about it. I'll make it big N actually. And the energies of the particles are, the momentum of the particles rather, are any old values of the momenta, provided this thing adds up to some value u. And if you think about it, the condition that the sum of the squares of the momenta divided by some constant amount equals a certain amount just says that the particles lie on a sphere in the momentum bit of the phase space. What's the surface area of a sphere? Well, up to some geometric constant, it's equal to the radius of the sphere to the power of the dimension of the bit of the space minus 1. Yeah?
I'm sorry, can you explain the sphere bit again?
Yeah, sure. So let's think about one particle, yeah? I've got one particle, and I know its total energy is E, say, or U in this framework. So it's got momentum P in the x direction, P in the y direction, P in the z direction. Its total energy is the sum of the squares of momentum divided by 2m, because half mv squared and P equals mv, so half mv squared is p squared over 2m. So the sum of px squared over 2m plus py squared over 2m plus pz squared over 2m is 1 over 2m times px squared plus py squared plus pz squared, which is 1 over 2m times the radius squared in the space. So I've got a constraint to lie on a sphere. So...
Are you sure?
Yeah,
That was
so
pretty fast. Yeah.
if I've got 2 or 3 particles, I've got the same story going on, just in a larger space.
So the sphere is the 6n dimensional or the 3n dimensional?
3n is the meant to be. Yeah, exactly.
Yeah.
So if I've got one particle, then the surface of the sphere is going to be 4 pi times the radius squared. You can kind of see on dimensional grounds that if I have a sphere in a higher dimensional space, then the surface area of the sphere is going to be some geometric term up front, filling in for the role of the 4 pi piece, times the dimension of the space minus 1, times the radius to the power of the dimension of the space minus 1. So a sphere in 4 dimensions is going to have a surface area proportional to r cubed, in 5 dimensions proportional to r4, and so on. And if you want to take the degenerate case of that, a sphere in 2 dimensions is just a fancy word for a circle. And so the surface quote area of the circle is just a fancy word for the circumference, and the circumference is just proportional to r, which is r squared r to 2 minus 1. Okay, so I've got a sphere, its radius, the square of its radius is 2mu, because I've got sum over I, pi dot pi over 2m equals u. Multiply, bring the 2m over to this side. I've got the requirement, the sum of all of the squares of the momenta is 2mu. So I've got a sphere in 3n dimensional space, very high dimensional space, and the radius of the sphere is the square root of 2m. So what's the volume of the sphere? Well, it's the radius of the sphere to the power of 3n minus 1. What's the radius of the sphere? It's the square root of 2mu. So I'm looking at volume of the sphere in space equals root 2mu to the power of 3n minus 1. So
That's the volume of the shell, the sphere surface.
Sphere surface, yeah, sorry, sphere here means the thin shell as opposed to ball, which is the whole thing.
Right.
But yeah.
That's the surface of that sphere in P space. So,
That's right.
So you're gonna have to like then put in the.
Exactly. So now we bring back that bit we had left over from X space, because the particles can have any position they like, and we get out that the density of states function for the whole thing has that form, right?
There's some constant at the front, isn't there?
Oh yeah, sorry, thank you. Why don't you care about the constant?
Because the log's going to...
Because I'm going to take a log of it, exactly. Yeah. Log of something times a constant is just log of the something plus a constant. And my definition here really ought to have a plus constant anyway. Okay, so notice, I mean, that's a little bit abstract. You have to think about it for a moment, but we get to it really quite quickly from the starting assumptions. Let me just do that. Well, actually, two things to observe first is I've moved to just writing this as a function of volume, and there's a bit of a cheat going on there in a sense, because I originally said that the Hamiltonian of the system could depend on a bunch of parameters and maybe depend on the length and the breadth and the height. But those parameters only came in because they told us where were the possible positions the system could occupy. As far as phase space volume is concerned, all we care about that is the total volume. So we've already got out the fact that the density of states function doesn't really depend on the length and breadth and height of the box at all, it just depends on the volume of the box. So we've already got out the fact that, I mean, given this completely undefended as yet assumption, we've got out the fact that the equation of state of the system is only going to have the energy and the volume as parameters in it, not the energy and the length and the breadth and the height. And you can perfectly well imagine, solids of various kinds where that wouldn't be a safe assumption, or things with springs in or something wouldn't be safe, but for this system it's safe. So S of UV is now just the logarithm of that thing. Okay, so how will people remember their logs? If I take the log of A times B, I get the log of A plus the log of B. If I take the log of something to the power n, I just get n times the log of the something. So the log of that is just equal to n log V plus and since n is big, n is about 10 to the power of 20, then the difference between 3 times 10 to the power of 20 minus 1 and 3 times 10 to the power of 20 is not such that you much care. So unless we're working to 20 decimal places, then you can approximate that as 3n over 2, and this is does that look familiar? Remind me, where have we seen that already?
State function. So.
Yeah, it's the original state function. Originally we just wrote the state function down, so we've confirmed that using recipe 1 of statistical mechanics just returns us the state function that we're after. In fact, we've done a little bit better than that, because where we put the state function before, this 3/2 term was just left as the as an unknown constant. Well, a constant which had a thermodynamic interpretation, but intrinsically a constant. So for this monatomic gas, we've got that number out. And in fact, if the gas had been diatomic particles which had been able to, have internal energy levels, we'd have got out a different number. So the technology there delivers the empirically correct answer. And you often don't get very far beyond that example in an undergraduate stat mech course, but you might end up looking and seeing we can do the equation of state for a radiation bath in the same kind of way. Do the equation, if you do a solid state course, you might find you do the equation of state of, say, a low temperature crystal in similar ways. All these are quite easy systems, but you can run these kind of calculations for enormously harder systems. An enormous fraction of equilibrium statistical mechanics is concerned with the calculational machinery of working out these things. And when we do it, as far as I know, whenever we do it, the answers that we get out from that process match to within the accuracies of experiment and calculation. They match the empirically measured thermodynamic potentials. The technology works. That was step one for the recipe.
Could I add one short question? Of course, you can add the statement that n is enormously large and that n and n minus 1 are almost the same. But there's nothing in the machinery that dependent on n being large. We could even go to the extreme that n is 1, as you in fact did for the harmonic oscillator. Would we still get, I mean, of course it's not very easy to talk about the specific heat of one part of the gas. But in that case, of course, the difference between 3/2 or 2/2 would be considerable.
It's a good question, and it turns on some of the issues that just to what extent statistical mechanics is applicable to very, very small systems. I think the answer is that in most circumstances, this is jumping ahead a little bit, but in most circumstances where you'd allow a very small system like that to equilibrate, the relevant thermodynamics you'd be using would be the canonical rather than the microcanonical version. For people who know the framework, this is the microcanonical version of statistical mechanics. There's a canonical version, which I'm skipping for time and simplicity, really. I think if you do the calculation in the canonical version, you won't have the -1 factor knocking around. I'm not certain. Don't you? I wouldn't bet my life on that. I'm fairly sure that's right.
But I think it is worth flagging. If you want to talk about statistical mechanics as actually practiced, then like it's rife with large n approximations, and it's a real question how much of the machinery applies to when you're inside that machine.
But it is an interesting flag. The formalism, as when I'm making the claims about this technology works, the applications I'm thinking of tend to be largish systems, but not exclusively. You need to do some clever trickery with this formulation, with this kind of framework to handle small n systems. Let me leave the question about exactly how that works until we've got kind of more machinery to talk with them. Okay, that was the step one bit. That was how we get our equations of state in the recipe of equilibrium thermodynamics. We also wanted to know, I suggested, how the various properties of a system of equilibrium, other than its state function, are determined by its underlying physics. And that's step 2 of the recipe.
Are you using the equation of state and state function interchangeably?
Yeah. Where the calling function equation is causing some trouble, yeah. State function here tacitly meaning function of some given variable and the rest. It's I'm losing my terminology in this. Step 2 works like this. Step 2, and I've stated this relatively carefully or cautiously, to calculate the result of any measurement you make on a system at equilibrium, do the calculation as you would do it if the system's real state was randomly chosen from all of the points on the energy hypersurface, with the probability of it being in any little volume inside the hypersurface being proportional to the volume of that little volume in the phase space, with respect to the legal measure of phase space, if you want to know which volume. Now, I haven't said that it's an assumption of equilibrium statistical mechanics that is true. That's highly contentious. I have said that if you want to get the result of a measurement, you should pretend it's true and calculate on that basis. That's how the machinery of the game is done.
Do you mean when you said proceed as if take an average of all of them?
Well, how would you proceed in that situation? One thing you might do is you might take an average. One thing you might do is you might work out the variance, find it's very incredibly low, and so assume that the probability will be the average. So it's going to depend what thing you want to do. So as a special case of that, to calculate the result you would expect to observe on average on a long series of measurements, do exactly as you said, average over the surface.
So we can also have a probability distribution.
Not only to calculate the result of the measurement, but to calculate the probability of the result.
Yeah, yeah. So I'm not restricting my attention here to averages. And in fact, let me do a quick illustration to show that. Suppose we have our, go back to our ideal gas again, and suppose I've got one particular atom in the gas, and let's just suppose it's tagged, you know, it's radioactive, so I can tell which atom it is. This is highly implausible in practice, but somehow I can tell which particular atom I'm interested in. And I want to know, if at equilibrium I measure the velocity of that atom, what's the probability of me getting a particular result of that atom's velocity? In particular, let's say, sorry. No. So in particular, let's say all I care about is the x momentum of this atom here, and the x position of this atom here. The formula says if I want to know what I should expect on making that measurement, I should use that. So it's dead easy for position, for instance. The uniform distribution over the energy hypersurface would say that that particular atom is as likely to be in one place on the surface as anywhere else on the surface. So it would say that I should expect to find the particle randomly anywhere in space, and I should find it equally likely that it should be in any region of space. And if you imagine, if you parlay that up to the positions of a whole bunch of atoms, you can see just by thinking about the combinatorics, that's going to tell you that what step 2 says about what you should expect about the kind of distribution of particles across space in the box is, you know, if each particle is equally likely to be anywhere in the box, then given there's vast numbers of the particles, then the probability is enormously high that the distribution of particles across the box is pretty much uniform. So I should expect to an enormously high degree of confidence that when I measure how uniform the gas is, I should find it uniform. That's what the formula, that's what the recipe tells me to do. That's what I find empirically. So the recipe's got maths there. Yeah.
Just a slight point. I mean, isn't it? I was thinking that these distribution, I mean, to the same nicety as before, the distribution is not uniform over the hypersurface, but it's also have to divide by the gradient of the Hamiltonian. Right?
Yeah, so by hypersurface, what I really mean here is hypersurface of very, very small thickness. I don't mean the literal zero surface. So I'm continuing universally here to avoid getting caught up in mathematical fiddliness to say when I mean hypersurface, I don't mean a surface of zero thickness, I mean a surface of a fixed, very small thickness. 10 to the minus.
I'm just asking because...
No, it's what you might check. Yeah. It's 10 to the minus my phone number, joules thick. And yeah, if you didn't have that, if you literally work in terms of the surface, then you're right, you need a term on the surface that was proportional to the gradient of the energy normal to the surface. Okay, so staying with position for a minute, I've got a whole bunch of particles' positions, so I've said, you know, enormously high probability I should expect that the distribution is going to be uniform. How high probability? I could take a little cell in the gas, you know, a micron across, let's say, and I could ask what's the probability of finding the density of particles in that bit of the cell a bit higher or a bit lower than the average density of the box. I could ask what's the standard deviation of measurements made on the distribution of density in that box. And the formalism, I won't work this one through, but the formalism will give me an answer for that, and it gives me an answer that's confirmed by experiment. To be honest, I don't actually know if fluctuation phenomena of that kind have been confirmed in ideal gases. They're confirmed all over the place in other statistical mechanical systems. What about momenta? So I've got my one particle. I want to know how fast it's going in this direction. Well, remember that the momenta are distributed across this sphere in momentum space of a particular given radius, which is 2mu. And let's suppose that the in fact, actually, let's do the whole. No, let's stick with this one momentum. So let's suppose that the momentum of the particle in the x direction is just p. So visualize this for a second. If you imagine a three-dimensional sphere, and I pick one of the directions, and I say I know what it is, and I ask what's the surface area of the sphere consistent with that assumption, plus or minus a little bit, then I'm going to have a little circle in the sphere of a radius that's going to be given by, its square is going to be the square of the original radius minus the square of the term I've already got. I'm going to, yeah. So in 3 dimensions, x, y, z, this points on this surface are the points where px squared over 2m plus py squared over 2m plus pz squared over 2m equals u. So if I restrict my attention to the assumption that px has some particular value, that's going to fix me to some, or particular value plus or minus a little bit. It's going to restrict my attention to a little strip on the surface. What's the radius of that strip going to be? Well, it's going to be the original full radius here squared minus this bit here squared. This thing, which is the squared momentum of the particle, the first particle, plus this thing, which is the radius of the circle, squared equals this thing, which is the radius of the original sphere. So if I want to work out what the region of the energy hypersurface is consistent with the assumption that the original particle has x momentum p, I no longer want to know the surface area of a sphere of radius squared 2mu, 3n minus 1 dimensional. I now want to know the area of a sphere radius squared 2mu minus p squared with 1 fewer dimension. So if I call that thing, say, volume subscript p, it's going to be proportional to square root of 2mu minus p squared 3n minus 2. And that thing is proportional again to, sorry, the 2 I've double counted. I just pulled something out. But by the way, if you're not following the fine detail of this calculation, don't worry too much. I'm just doing it for the illustration of the fact that you can just do things with this machinery very fast and very powerfully. The actual fine details of how I'm doing the calculation is not completely crucial.
So you've absorbed the mass of the...
Yeah, I just divided this thing. Because it's proportionality, I can just divide through by a particular thing if I like. This thing doesn't depend on the p. That's just multiplying and dividing by the same thing. The reason I've done that is because what's that equal to roughly if n is big?
Minus x.
Yeah. So what we work out is that to a very good approximation, the probability of the particle being found with an x position, x momentum, in the vicinity of p is equal to e to the minus this term times p squared. So we have an exponential dependence of the probability of finding a particular particle with a given momentum given by this e to the minus p squared function, which you probably remember, anyone who's done a kinetic theory course, as Maxwell's distribution for the probability of finding a given particle in a gas as having a particular momentum. And if you play around with that number and you approximate 3n minus 2 as 3n, you'll find that this actually gives you quantitatively out the right form of that expression, but I'll leave that as an exercise.
Is that one component of momentum? So it's one
component.
direction? Yeah,
that's exactly right. But if you now multiply those three together for the three components of momentum, and then you're going to get out the formula in energy that you're used to. The maths doesn't really care whether any given two p's are different momentum components of the same particle, momentum of different particles. As far the theory is mathematically equivalent to 3n particles in one dimension.
It's not the probability of the overall momentum being p, because you need to have a piece of fact at the front of the.
Exactly. Yeah, exactly. This is the x component of the momentum. I mean, that's right. So there's no usual density of states thing you get. That's why I did it one component.
But we're using the Stargate approximation, the x and y and z components are independent, so you get to multiply them together.
Exactly. And what I care about is the fraction of particles I should expect to have given velocities. I can get that from, I can just, this calculation didn't suppose a particular particle, so the average value I get in measuring these things would give these as the fraction of the particles which have a given momentum. If I'm interested in fluctuations around that, I can do it. Notice that this is a probabilistic number of the kind of thing I don't remotely see in equilibrium thermodynamics. I'm just getting it out from the machine. So, okay, so here's the point to take home. These are basically the two moves made in equilibrium statistical mechanics. The basically is hedging over certain other techniques that get used, but basically this is the technology that is used. It is the project, I think, of foundations of statistical mechanics, of equilibrium statistical mechanics, at least in part, to understand why that machinery is right. This machinery by itself, even if you knew it was true, does not directly give you grounds to understand the laws of thermodynamics. You have an additional task in play there. But equally, it's important to hold on to the fact that a large part of what statistical mechanics is conceptually, and an enormous part of what statistical mechanics is in terms of what people do with it, is this kind of material. So keep that in mind, trying to read various routes to the foundation of statistical mechanics. See whether it delivers for you not just qualitative results like systems go to equilibrium or the second law holds, but quantitative results like this is how you calculate a state function. Yeah, yes.
Well, I think this is perhaps the right time to raise some question or suggestion.
Some ways.
It's. I mean, you can think of statistical mechanics, equilibrium statistical mechanics, in different ways, and so you started out with saying it's wrong to think of it as a foundational project. I think I agree to a large extent. I'm not quite sure what the alternative point of view would be. But I will certainly agree that one of the main claims to fame of statistical mechanics is that it's a machinery that produces models for concrete systems, which if you follow the recipe, you can give a thermodynamical description of in terms of what you call the equation of state. And that gives you all the thermodynamical properties that the system would have if it was realized in a new world. Okay. And so that's extremely useful and extremely powerful. Whether it's also a project that should found thermodynamics or not is perhaps a second issue.
Yeah, I mean, I make no claim here.
And even if it's a project that would be conceived as a foundation of thermodynamics, that would still leave open, certainly, the next question, whether statistical mechanics itself is in need of foundation. I mean, in my point of view, every theory has foundations. It's not that they're in need of foundations. Every theory it's useful to think about fundamental questions, and doing that is studying the foundations of the theory.
I don't think you said anything I disagree with, but you expressed it as if I ought to. It sounded,
No. I'm just curious whether you would agree with that, because I heard you denounce that statistical mechanics was a foundational project. I didn't quite hear you explicitly say what the alternative point of view was that you.
Okay, good. So let me say this explicitly. What would we like to do in statistical mechanics, and what do we partly do? Claim that the construal of statistical mechanics as a foundational project. What I mean by that is that what we want statistical mechanics to do is to deliver a microphysical foundation for the laws of thermodynamics. Claim I'm making is what we'd like statistical mechanics to do is, as well as doing that, to give us a grounding for the large amount of calculational results that statistical mechanics has. The task in the philosophy literature of trying to find foundations of statistical mechanics seems to align the task of providing a foundation for statistical mechanics with the task of providing a statistical mechanical foundation for thermodynamics. This is by no means universally true, right? This is often the impression one can get, and I think particularly one can get at a kind of pedagogical starting level into it. So there is a need to understand the foundations of statistical mechanics, by virtue of which things of this kind turn out right. Insofar as this is just a black box recipe and not something we can understand in terms of the underlying microphysics and in terms of and whatever other assumptions we need to make understood explicitly, then we're not done with the foundations of statistical mechanics. It might logically be the case that we could be completely done with that task and still be left unclear as to how to solve the foundations of thermodynamics problem. It's logically possible that's the case, it's also logically possible the contrary is the case.
I guess I want to understand the vocabulary a little more clearly. Is a case of, say, reducing theory B to theory a case of giving foundations, of showing how theory A gives a foundation for theory B, or is there something more that one would want?
That sounds good. Did I use the term reducing?
No, you didn't. I'm trying to understand what it sounded like you were saying. Recipes like these could potentially be a way to get all the thermodynamics.
Oh no. Oh. So this is a recipe. I mean, almost by definition, this can't give you a conceptual grounding for thermodynamics because it's just a calculation.
No. That's not. But I didn't get to the end of my question.
Oh, sorry.
Suppose that it were the case that from recipes like these we could get all the thermodynamic laws, and suppose further that it was the case that we had in hand what you're calling a foundation for statistical mechanics. That is a reason for seeing what justifies these recipes.
Yeah.
It seemed like you were saying even then we might not have in hand what it would be appropriate to call a foundation for thermodynamics.
Oh,
or did I mishear you?
You misheard me, or I misspoke. So given your conditional, then that's right. But it might be, and in fact I think is, the case that those recipes by themselves don't offer a conceptual grounding of thermodynamics. I think in a sense they're just too structured.
Yeah, no, of course. Yeah.
But it might be that supposing carrying out the project of understanding statistical mechanics, one advanced far enough along that project that one understood why these recipes are correct.
Right.
It might or it might not be the case that in doing so you had also advanced far enough that you could understand why the principles of thermodynamics are true. The converse is also right. One observation I have about a lot of the literature and the foundations of statistical mechanics is it tends to be very committed to the other task and very much engaged with the question about about trying to provide the foundation for the principles of thermodynamics, without much acknowledgement of the other things that statistical mechanics is in the business of doing. That, done with one's eyes open, that's an entirely defensible strategy.
Right.
I think often it's not done with one's eyes open.
Right.
But it is true, however, that if you follow this recipe and you think of that function as representing the entropy, you will get at least all the part of equilibrium statistical mechanics to hold automatically true.
Well, let me get from that a little bit. I mean, I don't see how you could get from that, for instance, the fact that if I vary the parameters of the system, allow it to come, causing it to leave equilibrium and allow it to equilibrate,
No,
so it's going to require increased entropy. Yeah.
The minus first law is non-equilibrium.
Right, but also the second law, I think. I mean, do you think I can get the second law from those?
The part that only deals with equilibrium, yes, but that part is just a statement that S hasn't, that DQ is...
Oh, I see what you mean, yes, sorry, yeah, sure, you'll certainly get out du equals minus PdV plus ds, yeah, sure, agreed. But in a certain sense, I mean, the problem is if you're not careful there, that can almost become analytic. I mean, if T is just by definition the rate of change of energy with entropy at constant volume, and if P is just by definition minus the rate of change of energy with volume at constant entropy, then sure you can get out du minus PdV plus TdS, but it's just, I mean, then it just becomes an analytic claim. I mean, I take it some of the conceptual content of P minus PdV plus TdS is that the minus PdV is the work, and TdS is the heat. So, and I don't think I'll get out the fact that TdS will be the heat flow if I put systems in thermal contact. So that's the sense in which I think this doesn't finish the story. Okay, I'm going to forward straight on to non-equilibrium statistical mechanics next. Are we at the right point to take a break? Okay, let's talk about the non-equilibrium case. So, let me kind of recapitulate my kind of more than foundations propaganda spiel that I had for equilibrium statistical mechanics. It's tempting, if you've just got thermodynamics in mind, to think that the basic empirical fact we want explained is that systems not initiate equilibrium go to equilibrium. And so the task of non-equilibrium statistical mechanics is completed once we have an appropriate argument that tells us that systems do indeed approach equilibrium, given whatever additional side conditions are needed. But non-equilibrium statistical mechanics is generally concerned not simply with the qualitative fact that certain systems go to equilibrium, but with quantitative facts about how fast they go to equilibrium, what states they pass through on the way to equilibrium, what the circumstances are in which they don't go to equilibrium, and so on and so forth. So, for instance, just to recapitulate an example I kind of mentioned in passing earlier, the air in this room would quite like to be iron. It is thermodynamically favourable. If you're in cold places like this room or the hearts of stars, then it's thermodynamically favourable for things that are lighter than iron to fuse into things that are iron. In really hot places like the early universe, that's not true, but in cold places like stars, it's true. Why don't the atoms in this room fuse into iron? We understand perfectly well why. We have a detailed dynamical explanation. It's that the kind of collisions between oxygen atoms that would allow them to fuse would require that the Coulomb barrier between nuclei is overcome. You know, if I get two nuclei really, really close together, the strong nuclear force takes over. But prior to that point, there's electromagnetic repulsion. It's kind of strong at 10 to the minus 14 meters separation. So you need quite a lot of oomph to get things glided together in a way that allows them to react. So we have a straightforward dynamical explanation, but we need to understand how to plug dynamical explanations of that kind into a proper theory of equilibrium. And more generally, it is a observational case that we know a whole lot about equations that govern systems away from equilibrium and tell us how their properties evolve over time, and as they're left to themselves, they interact with various ways. So here's a very, I guess pretty much the earliest example of such an equation that purported to have microphysical foundation. So this is the Boltzmann equation. In Boltzmann, or in a slightly anachronistic formalism, in Boltzmann's original conception of it, rho was to mean modulo certain technical concerns and cares, something like the fraction of particles in a spatially uniform gas with a velocity in the think of this as a vector with a velocity in the vicinity of the velocity field. In a modern interpretation that you see rather more commonly now, but not universally, interpret rho instead as being the probability that any given particle will be found to have that velocity. Because of the law of large numbers, we'd expect these two to be extremely close to one another calculationally, even if conceptually very different. Boltzmann's equation, therefore, purports to tell us how the velocity distribution of a gas over time evolves. It has a number of extremely nice properties from that perspective. Notably, we can prove that its only stationary state is the Maxwellian distribution of velocities, and that therefore that if you leave it away from that state, actually not therefore, but in fact if you leave it away from that state, it converges towards that state in a certain fairly well-defined way. Yeah, modulo usual physicist cavalierness about mathematical precision. Given a system governed by the Boltzmann equation, we're happy with how to handle it. There are, for that very reason, profound reasons to think that it's very problematic indeed to suppose that the Boltzmann equation is in any salient sense derived from the underlying microscopic physics. I think Jos is going to talk quite a bit about that tomorrow, so I won't say very much about it now. Think of this as a placeholder. But I'm going to ask us to proceed in a minute in blithe disregard for the fact that we know something is profoundly wrong with the idea that this equation can indeed be derived from the microphysics, and ask how we would go about, on the assumption that it could be derived from the microphysics, what the kind of moves we could make in deriving it would look like.
David,
yeah.
Be just a tiny bit less coy. I mean, the obvious reason we have for thinking that it couldn't be is the time reversal symmetry of the right. Okay.
Yeah, time reversal and recurrence.
Right. Good. Good.
Right. So yes, to be a little less coy, this equation has a definite temporal directionality to it. The underlying physics doesn't, so we can't just mechanically derive it. Okay. Here is an interesting observation. It cannot be that we can apply an algorithm that mechanically derives the Boltzmann equation from the underlying dynamics. We seem to apply something that looks a hell of a lot like what we would do if it was possible to derive the Boltzmann equation from the underlying microdynamics. That equation, that process gives us an equation which works empirically. There's a certain temptation, if you're not careful in reading about foundation statistical mechanics, to think that Boltzmann's equation was an early heroic failed attempt, now superseded to understand the approach to equilibrium. Let me just quickly read it. So this is from a 1988 survey of applications of the Boltzmann equation. The introduction there is something like, the equations proved fruitful not only for the study of the classical gases Boltzmann had in mind, but also properly generalized for electron transport in nuclear reactors, photon transport in superfluids, radiative transport in planetary and stellar atmospheres. I might add from that it's also fairly relevant to the kinetic theory of galaxies. If you want to embed that result about nuclear fusion results I was talking about earlier in a mechanical context, you tend to embed it in the Boltzmann equation or various generalizations of it. It's crucially important to keep in mind that whatever the foundational problems with this equation is empirically accurate. It's thoroughly confirmed in a very wide variety of situations. And a whole bunch of other such things are also empirically confirmed and are derived in kind of similar ways. There's not anything like, I think this is fair to say, it's not anything like the same rather fairly cleanly stated calculational algorithm underpinning non-equilibrium statistical mechanics that we saw in equilibrium statistical mechanics, but nonetheless there are commonalities you can observe over quite a wide fraction of methods used to derive non-equilibrium dynamics. And I want to just kind of spell out how that works a little initially at least again in a fairly just black box way, and then kind of reflect a little about how the world could be if machinery of this kind is working. Okay, so let me get started on that project. And I'm not going to come back and look at the details of the Boltzmann equation except briefly and qualitatively towards the end of seminar. Let's set the problem up very abstractly. What's going on with an equation like this? This is not an equation that is tracking the full behavior of the system. The full behavior of the system is described by the positions and momenta of every single particle in the gas. This is something which firstly just threw the positions under the bus, and secondly is only interested in the velocities insofar as we're tracking averages of those velocities over very large numbers of particles. And in general, that tends to be the characterization of the non-equilibrium equations we see in statistical mechanics. We're interested in tracking only a relatively small collective number of the degrees of freedom of a system which has many, many larger degrees, many more degrees of freedom than that. In a sense, I think you can actually, and this now I think is philosophically contentious, though possibly not in this audience, you can actually to some extent characterize statistical mechanics in general that way, as an enterprise which is interested in the dynamical things that can be said about the collective degrees of freedom of systems. So in the equilibrium statistical mechanical case, we're interested not in every last detail of where every particle is, but various collective claims about systems averaged over small volumes and so on. Let me kind of pause to just push in defense of that way of putting it, in a preliminary way, against something you often see in kind of textbook accounts of it. It's not uncommon to see it suggested that the reason in statistical mechanics we decide to look at averages over large numbers of degrees of freedom is something about what we're interested in. You sometimes say, people have a description that says something like, well, we're interested in these large-scale degrees of freedom. We're not interested in what the individual particles are doing. This is difficult to defend for the following reason. There are many macroscopic systems about which I do not give a damn. Water is presumably currently flowing in various rivers somewhere in the Amazon jungle. I have no idea how it's doing it. I'm uninterested in what it's doing it. The mere fact that I am uninterested in what that water is doing in no way undermines the fact that the behavior of the water in the forest of the Amazon, I take it, is what's given to us by the collective principles of statistical mechanics. Conversely, I might be keenly interested in some particular feature of a system, and not at all interested in all the other features there. That doesn't in any way give me give the consequence that I can write down some kind of stable autonomous dynamics for that fact about the system alone. Otherwise it would make love triangles a lot easier, I suppose. Yeah. I'm not interested in the other guy in the picture. Okay, here's another thing that people say that about why we're interested, why we study these kind of collective degrees of freedom. And the other thing we sometimes hear said is something like, well, we would like to study the full description of the system, but we don't possess the technology to measure exactly what the particles are doing and to record it. Even if we did, we wouldn't be able to solve the equations of the system, so we resort to statistical mechanics as a kind of second best move. Here's an inconclusive but suggested worry about that. Let's suppose space aliens arrive and we tell them, and they want to know about our physics. And we say to them, we have this thing called statistical mechanics. And they say, okay, that's interesting, tell us about it. We're interested in the ancient history of science. And we say, well, it's a technique for calculating collective properties of large systems. And they say, well, why are you interested in doing that? And we say, well, because calculating, working out, measuring the exact positions of all the particles in even, say, a gas is too difficult for us. And they say, oh, well, okay, that's interesting. It's not too difficult for us. We have very advanced technology. And they bring down a machine, and we say, okay, just put your box of gas in here, and it'll just print out on this series of memory sticks the exact location of all of the particles in the gas. And we say, well, okay, but even if we could measure that stuff, we don't have the calculational capability of working out what it's doing later. And they say, oh, that's fine, we have very good computers. This computer here is powerful enough to take all that information we just measured about the gas and work out where all the gas particles are going to be, according to laws of physics, in 10 seconds time. And if you think about it, that wouldn't be a situation where you'd want to stop using statistical mechanics. if what you want to know for a particular gas is what's the configuration of the particle in that gas in 10 seconds time, waiting 10 seconds is a fairly effective way of doing it. What we're interested in these situations is generalities, broader collective features of these systems, facts about the systems, real dynamical things about the systems which abstract away, which lift away from the underlying microdynamics. If that is what we're doing, yeah, David.
Wouldn't these aliens also be in a position to say, to answer questions with the same apparatus easily of the form, can you tell me if there are behaviors that are common to a fairly wide swath of possible exact micro-conditions of the gas right now?
Okay, so here's what they say back to you.
Yeah.
Come on, guys. We do have the technology to calculate what 10 to the 23 particles are going to do. But you want us to do 10 to the 10 to the 23? Give us a break.
Okay. Okay. I didn't understand we were being realistic.
within certain bounds. Yeah, I mean, it's a fair point. They're kind of going to be brute force supermoons of that kind of thing.
Right.
I mean, actually, to digress, to be semi-realistic here, I mean, I don't actually know if this is a situation that really comes up, but, I mean, galaxies have order 10 to the 11 particles in it. My guess is it probably is drifting towards the capabilities of conventional supercomputers to simulate every particle in the galaxy. We wouldn't thereby want to abstract away from the desire to understand the kind of general dynamical principles governing what galaxies do. If we had a machine that could do 10 to the 10 to the 11, that might be a little bit different, but of course that really is a step beyond. Oh, okay, so here's a fairly abstract way of presenting that question of what collective degrees of freedom will look like, and we'll bring it back to the physics a little bit further along. So, suppose we've got something like this. We've got an underlying...
So there's this, story about, why the standard things people say about why we're doing statistical mechanics, shouldn't be the way we think about it. But in your view, then why are we doing statistical mechanics? Because we want to understand what the systematic tendencies between these macroscopic degrees of freedom.
Yeah, I mean, let me dwell on that a bit, because it's probably worth it. Let me break my rule of not coming back to the Boltzmann equation and say something there. So the Boltz, assume for a given system that the Boltzmann equation, abstract away the concerns about it, describes the behavior of the averages of the system over a certain period of time. Now, if we knew that for any given microstate, we knew the behavior of the individual particles at that time, we could presumably read off the behavior of the average distribution. But it's a somewhat striking feature that we can actually write down autonomous equations for the behavior of those collective degrees of freedom that abstract away from the details of the microscopic degrees of freedom, fugitively at least, there are statistical mechanical caveats lurking here. That abstract away from it in such a way that we didn't need to know those details except insofar as they determine the macro details. I mean, let me give another example of that, and then I'll show you how that works in the machinery I want to give you. So if you think about, here's a nice simple example that isn't controversial. Think about the Earth-Moon system, okay? I mean, how many degrees of freedom does that system have?
I actually couldn't hear it.
Right, sorry, how many degrees of freedom does the Earth-Moon system have?
12.
Okay, I get 12. So why 12?
Three directions, positions.
So if you want to then send the central location of the moon, central location of the Earth, we're up to 12. Yeah, okay, any advance on 12?
Order next to 24.
Yeah, you can make that move. Why is that?
All the atoms.
Yeah. Kind of, you're slightly underestimating the size of the Earth. The principle's right. About 20 orders of magnitude missing. Right, the question is actually somewhat context relative. We can, to learn everything there is to say about the Earth and the Moon in every last detail, we need to track all of the excitation levels of all of the nuclei in all of the atoms in all of the bodies in the Earth and the Moon. But we can say quite a lot of the Earth and the Moon about that. By treating the Earth and the Moon as rigid bodies, rotating, we can say quite a lot. By treating the Earth and the Moon as points, we can say an awful lot. To an extremely high degree of accuracy, the dynamical behavior of the center of mass of the Earth and the Moon, treated as point particles, can be calculated in ignorance of what the rest of the system's doing. Not perfectly, there are tidal drag effects, there's a reason why the day gets longer and the moon's distance changes, but to a very high degree of approximation we can do that. We can understand quite well why we can do that. We can write the dynamics of a free particle down, and we can see that you can factorize out the central mass degree of freedom and track it separately. So for that system, we've got a relatively clear case where we can get out dynamics for certain collective features of the system that abstract away from what the rest of the degrees of freedom of the system are up to. And I want to sort of claim that that way of thinking about things is a helpful way to see what's going on in a lot of the stat mech derivations or quote derivations of collective degrees of freedom, approach to equilibrium kind of equations.
But that sounds a lot like one of the things you rejected at first, that there are certain properties that we're interested in and we're not really interested in the details. Like
oh, but this is what I've said is independent of interest. I might be totally uninterested in the movement of the central mass of the Earth. It's still the case, as just a fact about that dynamical system, that there are indeed dynamical equations for the central mass of the Earth and the central mass of the Moon that, which are autonomous from the micro degrees of freedom beyond their central mass. That's independent of how much I care about it.
Well,
yeah,
maybe just take but I agree completely that whether somebody is interested in anything is not a very good reason at all. I mean, you could simply be stupid by not being interested in something, or you could be right. But what really matters, of course, is something is relevant. Now, it's hard to define relevance in a precise way, but what certainly matters in many cases. And you used the right word. I mean, the question is whether you can have description for an equation of motion, or dynamics, if you call it that way, which is autonomous on a certain level of description.
Yeah.
And that's not something which is automatic. Thermodynamics by itself does not have any autonomous dynamics at all. I should have mentioned this morning, but the name dynamics is not very well, which is bound to mislead people when they talk about it.
Thermodynamics is nothing like hydrodynamics or chromodynamics.
Because it doesn't have dynamics. And Boltzmann equation, in spite of its difficulty, does tell us that a density will evolve in time, in rho, in terms of a complicated equation which happens to contain only that density function in 4 different times.
I'm going to wave my flag now, because just anticipating where I'm going, so that I can
that's an autonomous equation. And what it tells us is that in order to predict...
I'm actually going to cut you off if you don't mind, because that's probably where I'm going. I'll take advantage of Wayne's flag wave. Yeah, I think I agree with everything you're saying.
Yeah, sure. Okay, we agree.
Okay.
He's trying to save you work.
So let's have a framework to look at some of that stuff. So suppose we've got some dynamical system, call it the underlying system. Let's think about it really abstractly. It's got a state space. I've got a dynamical operation on it. U of t is any non-negative number. U of t, x of t is where x evolves through or is left for a time t. And I imagine I've got let's call it a reduced system. And all I want to say about that for the minute is it's got a state space camera up. And I've got a reduction map. So I could take any point in the underlying state, and I can map it through the reduction map to some reduced state space. And the idea here is, in the example we've been talking about, the state space might track all the degrees of freedom of the system. The reduced state space might be such that its points tell me some collective properties of the system. So many points in the underlying state space will be mapped to the same point in the reduced state space. So in the case of Boltzmann equation, our underlying state space might be the entire phase space, and the reduced state space is going to be something like the function on the one particle velocity space that just tell us what fraction of the particles have any given velocity, modulo various mathematical concerns about the precision of that and about the smoothness of functions and so on. In the case of the Earth-Moon system, say, the state space might be all the degrees of freedom of the Earth and the Moon, and the reduced state space might just be, say, that 12 degree of freedom system we were talking about, or even the 6 degree of freedom system if I just track the individual location. 12 by the way, right, so. Okay, and then the interesting question is the following. Can we find a reduced dynamics for the theory, which is to say, can we write down an actual dynamics for this reduced system that respects this reduction? So if you think I've got the, let's have a drawing of the set. Can I move this equilibrium piece down? So imagine here's my reduced space, sorry, my underlying space gamma. Here's my much more svelte reduced space gamma r. Now, given a point here in the underlying space, there'll be a dynamical trajectory determined by the dynamics, which tells me how that system evolves. And if I use the reduction map R to map that trajectory to here, I'll find a trajectory in the reduced space. So every sequence of states in the underlying space determines a sequence of states in the reduced state. It doesn't follow from that the dynamics on the underlying system induces the dynamics on the reduced state space. Why not? You're allowed. It's students' first chance.
The trajectory in the reduced state might intersect.
That's at least that. Yes, I think that's is the reason I think you're in a different garb. But yeah, here's how I would put it. There could be there's no reason why another point here, x prime, let's say, which is mapped to the same point in the reduced space by the map, should be the beginning of a dynamical trajectory which is mapped to the same point at the end of the process there. There's no reason at all that should be the case. These are arbitrary maps at the moment.
So your question might have been better stated as, does it induce a deterministic dynamics?
Yeah, sorry, I'm interpreting dynamics just by definitional fiat in the way I've set up there.
But you might have asked it more liberally. Even does it introduce a simple or interesting dynamics or something like that? That might have been.
I could have asked a lot of things. For the minute, it might not even induce a complicated and boring dynamics.
Right.
But sure, I mean, you might find situations where it did, but where there was no elegant or simple description.
Right.
But more strongly than that, it could be the dynamic that there's just no dynamical rule at all.
Right.
I mean, sure, in John's very minimalistic sense, if dynamics just means a way of dividing trajectories through the state space into allowed and not allowed trajectories, then in that very minimal sense, indeed it does. But in the stricter sense that it just tells me which trajectory the system evolves along, there's no guarantee of that at all. So the name of the game is we want to find what are the situations in which in which we do get a well-determined dynamics, which is to say, if we want to work out the reduced state of the system at some later time, we can do it either by we can do it by mapping from any given starting state that corresponds to the initial reduced state and evolving under the dynamics of that setup. So if that were the case, then any trajectories like this, where the initial point got mapped onto starting point here, would be a situation where the final point was mapped onto the same endpoint. Another way of putting the need for those dynamics is if there is a reduced dynamics, call that U reduced. So U, if I have x reduced of t equals U reduced of tx. If there is a reduced dynamics, it had better satisfy, right, essentially another way of putting the same requirement up to various mathematical niceties is going to be, can I find a dynamics which commutes with the operation of the projection map? Will it be a dynamics where I can get the same result either by evolving under the underlying dynamics and then applying reduction map, or by applying the reduction map right at the beginning and evolving under the reduced dynamics? Yeah, John.
My attention just lapsed for a moment. Can you tell me again what the U sub are? You said reduced dynamics, but you've also told us that you don't always have it.
Right, so this is an distance requirement. Can I find such a thing
Oh, I see.
which satisfies that condition?
Okay, so, all right. So you're just, imagine there were such a thing, what conditions would it have to meet?
Right, exactly. If I can find such a thing that satisfies this condition, then it's going to follow that I get the same dynamics in the reduced space by projecting it down through the map, irrespective of how I fill in the residual details. And conversely, if I do get the same result, however I fill in the residual details, that does determine a dynamics, in this formal sense of dynamics, on the underlying space, and I'll just give it a name. So this comes back to Joss's point that in this equation, I need to know rho, but I don't need to know anything else about the system. Modulo, as far as it's a correct description. Any kind of questions or worries about that general kind of concept of autonomous reduced dynamics? Yeah.
I'm curious as to whether there's going to be a recipe for finding one of these maps.
There is in about 5 minutes.
Great.
It's a good question. How do we go about finding something of this kind? Okay, so there's a technique used in the physics literature quite widely, not always called out by name, but quite often called out by name. And it's called the method of projections, and I think it's worth kind of just spelling out to see how these things are done. I'm going to leave that up so I've got my framework in place, and I'm going to use this board to talk about workings. And this board to draw on. So if you look at these points here, yeah, these x and x prime, there's a kind of, you can imagine a kind of space of points in the underlying space, all of which are mapped by the reduction map down to the same point. So, and you can think in general of the underlying phase space or state space being divided into regions. Each region corresponds to a single point in the reduced space. So, for instance, for the Boltzmann equation, each region is all of the different microconfigurations that lead to the same Boltzmann velocity distribution. So, really, we don't. If there's a dynamical reduction available to us, so if there's a well-defined dynamics for the reduced system, then we don't actually care where, for the purpose of working that out, we don't care where the system is within each given set of points that gets mapped to the same place, provided it's somewhere in that region. And in particular, if we wanted, we could just choose a representative point in every region that gets mapped to a single place. So, put that explicitly for every set. Like that. Yeah.
We also can consider cases where you have reduced dynamics which work not for all initial points in your initial state gamma, but I say that's coming in.
Okay. So do you see the idea here? There's a whole bunch of points, all of which correspond to the same average velocity distribution, for instance. The way I could describe that whole set of points just by saying, well, it's all the points of this distribution, or I could just describe them by a representative member of that set of points. So I could decide, for instance, that the point I want to use as the representative member of the set of all points, of all phase-space configurations of a given velocity distribution, is the one where the velocities, where the positions are fairly evenly distributed across the box. That would be one recipe I could use to choose my representative point. So I define a thing called a projection map. Which takes every state to its representative state. The reason I call it a projection map is you think about the definition of a projection in quantum mechanics. The projection map satisfies J squared equals J. Applying the map twice is the same as applying it once. That's what we mean by projection in maths. So the reason this is a projection is because it takes every point to its representative, every state to its representative, and so it takes its representative to itself. So it satisfies J squared, J. It also, because every point is a representative, because this takes each point to its representative, a point representative had better have the same reduced state as the original point. So we better have Rj equals R. I remember that, might I remember what the mathematical name for a condition of that kind is. And it would then be the case that J so if J gamma is just the space of representative points, so it's a subspace of the original phase space, then because I've got exactly one representative point for each of these guys, then there's going to be a one-to-one correspondence between that particular subspace and the reduced space. The point of all of this is I can do my dynamics in the original space, confining my attention to this set of representative points, rather than doing my dynamics in the reduced space.
What exactly is the symbol between?
Oh, I made it up, sorry. What I mean by that is in one-to-one correspondence between, there's a one-to-one correspondence between them, and this is the correspondence.
This is also under the assumption that the reduced dynamics is deterministic, otherwise.
All my dynamics is deterministic, yeah. So when I say, so I'm just for simplicity by dynamics, I mean deterministic dynamics. And I'm just kind of nothing to see about kind of weird violations of determinism or caustic points or phenomena of that kind. I'm just kind of glossing over those kind of concerns here.
Why is that correspondence not simply identity?
Because, well, I mean, just for a kind of brutally trivial fact, that gamma and gamma R are different spaces. No point lies in gamma.
On the left side, you use the projection map applied to all of gamma.
Yep.
And so what I get is that I can divide up gamma in each of those sets. On every set, they form a partition.
Yeah.
For every set, I will choose one of the representatives.
Yeah.
Are they still lying in gamma, right?
They still lie in gamma, exactly. Yeah.
But now, if I apply the reduction map,
yeah,
I will get equality.
Yes, that's exactly right. Yeah. So you can think about the set of these representatives, the image of the projection, as being a picture of the reduced space in the underlying space. It's a section of the vibration of the underlying space over the reduced space by the reduction map. If you don't know what that means, don't worry about it. Okay, so why am I doing this? Well, here's the reason. The reduced dynamics, by construction, if there is any such thing, does not care about what the underlying state is, except insofar as it lies in a particular representative. So, if I want to work out what the evolution of the reduced system is, the evolution of the reduced system is totally unbothered if from time to time, when letting the underlying system evolve, I just whack the system state with the projection map. Because the dynamics I get from proceeding from the point Jx, under reduction, is just the same as the dynamics I get proceeding from the point x. Every now and again, if I want to just move a point onto its representative, then it won't make any difference to the reduced dynamics. So imagine I start off with a state on the on J gamma, a state that's a representative state. I let it evolve. It wanders away from the space of representative states. If I just bang it back down to the space of representative states using the projection map, it won't make any difference to the reduced dynamics. So what follows from that is if there is a reduced dynamics of the kind we're looking for at all, then instead of looking at what I get if I apply the proper underlying dynamics U, I can look at this dynamics. So this dynamics, this UJ dynamics, call this the projective dynamics, is the dynamics I get if instead of evolving the underlying system just under its proper dynamics, I evolve it under its proper dynamics for some interval of time delta t, then I project it using the projection map, then I evolve it under delta t, then I project it, and I just keep doing that. So I've got a kind of zigzaggy motion where I alternate dynamics and projection. If there is genuine reduced dynamics, if there really is a reduction map and there really is autonomous dynamics, that should work if what I want to get out is the reduced dynamics. Let's be completely clear. There is no need in saying any of that to make any claim that what the system is really doing is being evolved by the projection map. The system in this story is continuing to evolve perfectly happily under the U dynamics. But for calculational purposes, I can, if I so choose, perfectly happily apply the projection map every now and again. Why might I choose to do that? Answer, because if I've chosen my representatives to be nice, simple states, it's probably the case that doing the dynamics in the close vicinity of the representative states is a lot simpler than doing it in full generality across the whole space. So if, for instance, my projection map projects me onto a situation where my particles are uniformly distributed across the box, then I can make all sorts of assumptions about how likely it is given collisions are going to happen, not likely in what fraction of collisions have a certain property, all sorts of assumptions like that just won't be true in full generality. And on the assumption there is a reduction map, there is a reduced dynamics at all, making those assumptions is harmless by construction. Yeah.
Well, it's not just assuming that there is a reduction map, but it's assuming that there is a reduced dynamics.
I'm sorry.
Because everything you just said
yes, I'm
is
sorry.
not things you have established.
Yes, no, I'm sorry. When I say Joss, I just misspoke. When I say reduction map, I mean reduced dynamics. Clearly, the fact that there is a reduction map is an utterly trivial claim. Any old map will do it. The map that takes the whole of phase space to the unit set consisting of me and David is a reduction map. It's just that there's unlikely to be any interesting dynamics defined by it. So yeah, another way you could put the terminology, you might say, so here's a bit of terminology you could say there is not, the reduction map is autonomous if there is a reduced dynamics. It leads to some interesting dynamics. That's the substantial claim. Insofar as that is true, if that is true, then we can evolve the system under this projected version of dynamics perfectly. Here's the claim. A very large fraction of the derivations done in the physics literature to work out what the reduced dynamics of collective degrees of freedom are has this form. It's done by this kind of technology. This kind of technology has some very attractive and unattractive features. One very often finds in the way that these things are set up that there will be some kind of property of the system that is invariant under the underlying dynamics and is strictly increasing, or strictly increasing except in certain circumstances, under the action of the J map. If that's true, then dynamics that you get out this way will have a certain strictly increasing property. And you'll be able to prove all sorts of thermodynamically nice things about dynamics of this kind. About the sense in which properties like something that can try to be a statistical mechanical correlative entropy can increase, properties about systems tending to certain states and staying there, all sorts of the kind of things that we like our non-equilibrium statistical mechanics to do. So this kind of thing has a lot of the mechanical properties we really like. So far so good, except that for reasons we've mentioned briefly before, and we'll talk about more throughout this week, we have powerful reasons to think that no such properties can be true in full generality of these systems. So here are two important observations from a philosophical point of view, one of which I think has more attention than the other. The first observation is that for the kind of projection maps that are used by physicists to do non-equilibrium statistical mechanics, equations are derived that cannot possibly be reductions in this strict sense of the underlying physics. And therefore, we can almost think about the equation got out as demonstrating that there is no such reduction in the strict sense. That fact is, I think, relatively widely understood in the philosophy literature. What perhaps is worth paying a bit more attention to is the fact that notwithstanding that, the equations that we get when we run this technology reliably work. They are reliably correct descriptions of systems, systems collective dynamics. So a lot of care and attention and thought and detail and delicacy in finding the right reduction map and the right way to set it up and the right way to avoid this thing leading to weird transient behavior and things. But using this kind of machinery gets us reliable equations. This method of projections is projectable in the philosopher's sense in a double way. Not only is it projectable in the sense that the individual equations we get out of it, like the Boltzmann equation, seem to be kind of projectable generalizations about systems, but the success of the method is projectable in the sense that if we apply it to new systems, it's got a pretty good track record. Well, the track record of trying it on systems we haven't tried it on before at the time has a pretty good track record of generating good equations for the system. Yes.
So I hate to interrupt you, but I missed something. Because I thought that just a minute or two ago, we were still talking about requirements that better had to be true for the existence of the reduced dynamics.
Yeah.
So these were this was just our wish list.
Yeah.
We didn't have anything to do.
Yeah.
And now you're talking about, oh, this recipe actually works and it is successful. And I get the impression like, we actually got all these things. But how did we get from just having our wish list to actually having the stuff we wish in our hands?
Okay, so there's two different things you might be asking. Let me pull those two apart. So one thing you might be asking is how do we choose the particular choices of J and R we're interested in? The right way to put this stuff works is that for a wide variety of systems, when we try things like, well, how about the low frequency degrees of freedom or the collectives across it? What about those kind of things? What about if we average over cells that are micron wide or so? Let's try that trick, shall we? Those are the kind of rough and ready means that we use to find it. The other thing you might be asking is, well, how should we think that those kind of technologies, doesn't the success of those kind of technologies all rely in the argument on the fact that there really was a reduction in that setup? And in a sense, yes, it does. And then the weird thing is it works anyway. Yeah.
Okay, I think. So what you said
could you speak up?
What you said is a bit confusing because doing this works.
Yeah.
Even though we don't, in fact, have dynamics to satisfy the criterion that you said.
Exactly.
dynamics does. And I think that needs to be said more explicitly, that for the reasons that you mentioned at the beginning, the reversibility and recurrence, there couldn't possibly be a reduced dynamics that satisfies those requirements.
Exactly.
And maybe it's worth illustrating it with the Boltzmann equation. The Boltzmann equation, you start with the reduction map goes from complete state of the gas to summary of how many molecules have velocities within certain limits. There's no way that there could be a reduced dynamics on that, because some of the states that share the same density function are going to lead to certain density functions, and some of the states that share that density function are going to lead to other density functions. Yeah.
So just check. So UJ won't in fact commute under the projection.
I'm not sure quite mean by project. You mean will it satisfy this kind of
yeah.
Well, it would satisfy it if this really was an autonomous reduction, if there really was some reduced dynamics.
Right.
Wayne's point, which is right, I should stress more clearly, is there are, because of issues of time reversal, there can't be such a map, not in the exact sense.
So it can't be, for the effectiveness of these methods, it can't be a requirement that you actually have reduced dynamics.
Right.
That's why I raised my point about the maybe being a partial map.
Exactly.
Even though it's not going to give you the same answers for all the initial states in that equivalence class, we might think that it's going to give us the same answers for the sorts of states that we actually expect gases to be in, something like that.
Yeah. Right. So this is exactly right. So here's a way of putting how this plays back into my kind of starting point of what's our problem here. In a way that I think is a lot less sharply stated in the literature, but has something of the same kind of this is a successful calculational recipe. We have a piece of technology which is used within non-equilibrium statistical mechanics to derive equations for collective degrees of freedom of systems. That technology has a certain motivation under which it would be true, which I've laid out. The motivation in which it would be true cannot be correct. The premises of that argument cannot be true. The result of the resulting technology, however, is nonetheless effective. So a major task for the foundations of non-equilibrium statistical mechanics is to understand quite why it is effective, given that the upfront reason it ought to be effective cannot be literally correct. Or put another way, to see what are the additional assumptions that must be coming into play. Yeah.
I think I know what you're talking about, but I just want to check. Could all this be put in the language of coarse graining?
That would be, well, J, one of the things you could choose as a projection map is coarse graining.
Yeah, I mean,
it's not the only available choice.
Because then maybe if I can just talk through an example, you can see why, contrary to all expectations, it actually works really well. So you start out, this is the process. We're going to have a compressed gas, which we then release into a vacuum, and it's going to fill the vacuum. Right? Now, the state of that gas in the full phase space is going to be represented by small volume in the phase space. Liouville's theorem is telling us that that volume can never change. Right? Volume is conserved. So what happens? Well, over the course of time, the volume sends out these little threads and tendrils that get, that start to fill up the space. Your J map here is then saying, oh look, the tendrils have been stretched out and they're filling up what looks like half the volume of the whole space available. But of course, it's an illusion because there are only just little tendrils everywhere. You hit it with this J map, and you now have moved it to the representative point of a space of a state that occupies the half.
Yeah.
So the idea is that as the expansion continues, you keep changing the reference class of the expanding gas into all the other gases that at a coarse grained level look like they have the same volume.
Yes.
Right, okay, good.
Yes,
I thought I got it. Right.
Here's the only caveat I put it that way. Although the coarse graining map tends to be the one that gets discussed a lot in these bits of the literature, I don't actually know any situations, which isn't to say there aren't any, I don't know any situations where the coarse graining map is parlayed up into a quantitative equation of this kind in play. The coarse grains that tend to be used in applications tend to involve integrating over other degrees of freedom rather than spreading into space. So I'm not sure, although formally you can fit coarse graining into this perfectly well, I wouldn't want people to think it's the only or even the most significant that comes into play.
But you also have subdynamics. But I'm sorry I'm coming back, but I still don't see, I mean, as far as I can see so far, this is a wish list. This is a set of requirements that you want a technique to fulfill. And you are speaking about it as if it is a technology, a proven piece of procedure that will lead us to success. I think there's a gap between the two. Just having a list of requirements that have to be fulfilled is not the same thing as actually finding a procedure that turns out to be successful in a reliable sense. And your requirements here have given us things that we want to have fulfilled, but it gives us no guidance so far in actually finding the maps we need to fill in so as to get the results.
So I think I'm repeating myself, but I probably want to be clear enough. Let me have another go. The way we proceed, the way this technology is applied, is we take an educated guess of the kind of projection we have in mind. We see if we get a dynamics using that kind of thing, which is pretty stable under small perturbations, how we did it, and variations in like delta t width here. If we get it, we run with it and we test it. That we have done a lot.
Yes. Yeah. But that's the. I mean, in the case of coarse graining, there have been these counterexamples of the spin echo experiment, where coarse graining doesn't work.
Yeah.
And so Van Kampen, who was one of the big advocates of this approach, said, well, you know, coarse graining is actually something that relies on the art and the insight of the physicist, because he, by his superior insight, is able to choose the coarse graining in just the right way so that it works. And perhaps this is a fair description of how physicists actually find the reduction maps or coarse grainings that actually work. And I grant it to him. Let's all be happy that they're able to do that. But it's not that this set of requirements explains us to us how they were able to do that. They were just lucky, or they were insightful, but we have no particular explanation how they were able to do that.
Well,
it just turned out to be
wait a second. I mean, there's one sense of this that is an unreasonable ask. I mean,
okay.
When I was doing my calculation earlier, I made a couple of mathematical manipulations. If you'd asked, how did I know ahead of making those manipulations that they were going to lead to good results?
Well, they didn't.
Please let me finish. They were going to lead to good results. Then I would have no good answer to give. I would have just said, well, you try lots of things, you see where you go. The fact that you can try lots of pieces of mathematical technology to see where you get is not going to be a legitimate worry of this kind. Here's the claim: when you find that you get a reliable, stable dynamics by thinking, ooh, let me try this version and run with it. The overwhelming, I'm not quite sure what I want to say about spin echo, but in the overwhelming majority of applications in physics, I can think, there are many dozens of cases where one tries this kind of machinery. You get out empirically reliable equations.
But you just described the Gibbs approach that he described this morning.
No, I don't think I am describing it.
Gibbs is coming tomorrow.
No, but Gibbs said if you give up the idea of finding the foundational empirical principles, it's okay just posit certain systems, and then when you get empirically good results out of them, then you can be happy with them.
No, I don't think that's quite right. I mean, suppose...
I was just quoting it.
Yeah, no, I don't think it's quite right that I am suggesting that way of doing things. I mean, suppose for the sake of argument that we didn't have our reason to think that the literal description I gave of there being a dynamical reduction and looking for it was the right way to go. If it really was the case that the activity we were engaged with in statistical mechanics was trying to find what the reduction maps are that genuinely exist, then the technique that says try to think of one, run it, and see if it works, I think is an entirely legitimate way of understanding it. It's not even clear to me that there is a residual philosophical problem in understanding that, if that's what I'm doing, any more than there's a residual philosophical problem, perhaps any less than there's a residual philosophical problem in asking how we know to try a particular manipulation or definition when doing a calculation in a physics problem. That's not the situation we're in. The problem we have is serious than that. Sorry, Wayne, you go.
I guess I kind of lost the thread of what's being said. So, I mean, if there were reduction maps that give to these reduced dynamics,
yeah,
then once we found one, there'd be no mystery as to why we're getting empirical success.
Yeah.
Now, what's a bit mysterious is that this method, in some cases, works even though there is, in fact, no such reduced dynamics.
Yeah.
That's
exactly right.
That's the question.
That's the deep concern.
Yeah.
Yeah.
Is the fact that the reduced dynamics that we practice, get and use is not time reversible typically, intimately connected to the fact that it doesn't satisfy your conditions?
Well, that's a very good question, and it's what I want to come on to really in the last part of what I want to talk about. I mean, so then the question is then going to be, okay, well, what kind of things can we be saying about a system that somehow means this is okay anyway? So here's a qualitative, very heuristic gloss about the kind of thing we might be saying mathematically if we find this kind of technology works. We could be saying something like this. And this is an intentionally vague way of putting it. It's a kind of prospectus for ways of thinking about the problem rather than the solution. Something like, somehow, states that are okay in some way, and in some way that being not okay is somehow a very special or annoying or detailed feature. States that are okay are within the subspace for which this kind of machinery works, and remain within the subspace for extremely long periods of time. And our kind of rough heuristic as to why that might be is going to be something like what we're doing in our reduction map, in our assumption that what we get at the reduced level is the same whether we use the representative state Jx or the original state X, is that we're assuming that all of the fine micro details of state X are somehow prepared to behave themselves and not do the kind of very carefully lining up in such a way that they keep the collective degrees of freedom around. But in some sense we can average out over them and ignore them in some way.
Whereas if your reduction map really was complete and obeyed these conditions, we'd be able to make good sense of the time reverse of reduction evolution, because we know that every state gets mapped to.
Yeah. Exactly. And look at an example of an exact reduction map. Look at the centre of mass of a freely moving body. Right. There it really is the case that our reduction map can take the system can take a system to its centre of mass state. It really is the case that we'll get an exact dynamics of the centre of mass state, and it really is the case that the dynamics of the centre of mass state are also reversible in time. So the relevant reversibility and recurrence properties of the underlying system are mirrored in the reduced system. If they were, the striking thing is that the machinery of constructing reduction maps is effective even though, precisely because we don't have those properties, it can't be truly reversible. And it does seem heuristically as if it's hard to see how that could be the case. Well, let me back off actually. Here are two reasons it could be the case. Here are two different sorts of reasons it could be the case. You might say internal and external reasons. So an internal reason might be that somehow, although this is not true universally, it's true for a very wide variety of states, that it's somehow legitimate or reasonable to assume that normally speaking states will satisfy this and will continue satisfying for long periods of time. And then the external reason would be something like this tells us that something was wrong with our assumption that the original dynamics were right. So if this kind of technology is working, but it can't work on the assumption the underlying dynamics of these properties, something's wrong with our assumption of the underlying dynamics. concrete ways you can try to realise that insight, for instance, is that you might suppose that somehow the application of this kind of projection or stirring it up kind of map is not simply, as I've defended it in the exegesis here, a mathematical move of no physical content, but is to be thought of as an actual physical transformation that happens. So, for instance, I think David will talk more about this later in the week, if you imagine messing up the state of the system by some kind of stochastic transition that's additional to the reversal dynamics of Newtonian physics, then that kind of framework delivers you a very, very different reason why this kind of technology works. So I want to just finish by just, because I don't think it's that widely known in the in this community, just to show a little bit of some of the machinery you get if you try to take that idea, that heuristic idea, and take it a little bit further. And this is more or less following a way of thinking about projection maps that Robert Zwanzig and various people developed in the 70s. So Zwanzig's interested in a particular case of these projection maps where the state space is linear. And the normal example where this comes up in statistical mechanics is that the great bulk of what we do with non-equilibrium statistical mechanics, as you might expect from equilibrium statistical mechanics, is we look at how probability distributions over phase space evolve, rather than how individual points in phase space evolve. How you want to think about that conceptually is a kind of deep problem, but just as a matter of what's going on in the community, that's normally how we model the non-equilibrium statistical mechanics. So to presage things, I'll say on Thursday, and other people may say at various points, there's then a profound philosophical conception about what those probabilities are. And if we want to think about statistical mechanics as a dynamical theory in some sense, we'd better think about those probabilities in a very objective kind of a way. But never mind that. For the moment, if the state space we're interested in, the underlying state space we're interested in, is a space of probability distributions over phase space, then it's got some linear structure on it, and we can ask that the projection map obeys that linear structure, so we can just use linear mechanics of various kinds to do things. So if we can do that, if we imagine our state is, the state of the system at some time is x t, we can break that state down into something like x of t equals j x of t plus 1 minus j x of t. And we're only actually interested from the point of view of getting the reduced dynamics and how this bit evolves. I mean, whether or not there is a reduced dynamics for this system, if all we're interested in is how the system evolves with respect to its collective degrees of freedom, then all we actually care about is this part. So, just to give us some terminology, let's call that part the relevant part of the state. And this part the irrelevant part. Relevant, that is to say that only this part is relevant to what the collective degrees of freedom are doing, and this part is not at all relevant to it. And we're assuming we've got some underlying dynamics, x of t equals u of t x. And let's, we could write that as a differential equation if we wanted to. We could have x dot of t equals u dot of t x equals u dot of t, u dot of t, u of t x. Don't worry if you're not following the details there. We can turn something like that into a differential equation that says what the rate of change of x is as a function of its current state. And it's then, I won't take you through the maths of this, particularly not at 5:30, but we can then actually, just as a formally exact mathematical result, write down an equation of motion for xr by itself. Now, if we could write down an equation of motion for xr by itself that only depended on xr itself at the start of time, it would have to follow from that we had a reduced dynamics. But we can work out formally an exact equation of motion for xr without making that assumption, so it must be true that that equation of motion somehow depends on the irrelevant part as well. Irrelevant in terms of the measure of the result of what the collective degrees of freedom are doing right now, but not necessarily irrelevant for what they're going to do later. And the schematic form of what we get looks something like this. The rate of change of the relevant part is equal to the sum of 3 terms. that's the form of these things, Z1, Z2, Z3, is quite complicated, but they have a specific closed form in terms of dynamics. This is a mathematically rigorous result for physicists' value of mathematically rigorous. There's a lot of epsilon, a lot of dotting of functional analysis you probably need to get it properly rigorous. I think you could actually make it rigorous fairly easily. I've got three terms of evolution. On the left-hand side I have how does the relevant part change over time. Remember, that's the only thing that's relevant to how the collective degrees of freedom of the system evolve over time. The first part is just, I mean, you can't tell this just from the form, but the first part is just an ordinary piece of reversible dynamics.
Let me just make sure I'm following you. So the relevant part is essentially the projection onto the representative state.
Exactly.
Is that right?
That's exactly right. The relevant part, R, if you like, could also stand for representative.
Right.
XR is the representative part.
Okay.
Yes, good, thank you.
Good.
So if you didn't have that stuff, then you would just have a nice friendly differential equation for XR. And that equation, in fact, would have no interesting time irreversible features. It's literally the projection of the evolution onto the representative subspace.
These are functions? Or
They have a particular closed operator form. I can show it to you.
Right, okay. They're not just coefficients or something.
No, they're fairly complicated operator functions of.
Right.
I mean, this one, in fact, is not even very complicated. It's the projection times the original time-dependent dynamical operator times the projection again.
Right.
So it's literally just double project.
Right. Right. Good. Good.
So the second term is non-local in time. It takes as input the irrelevant state at time naught. And the third term depends not only on the relevant state right now, but on the relevant state at various points over time. So it's history dependent in the sense that gets used in statistical dynamics. If you think about a differential equation, the evolution of the system now depends only on the rate of change of the system state now depends only on the system state now. If you've got something like this, it also depends on the system state at various early times. So people call this an integral differential equation. In fact, oddly enough, the kind of descriptions you get of determinism in the philosophy literature often much more suit that notion of dynamics. You know, normally we say we have determinism if the future evolution of the system depends on all of its previous states. Mostly what physics gets us is a situation that's stronger than that, where it only depends on its current state or its state over an infinitesimal interval of time. Okay, like I say, that's all formally exact, so nothing here can reliably tell us anything about irreversible dynamics or approach to equilibrium or anything. But it has an interesting suggestive form. The relevant part's evolution depends on the irrelevant part only via this term here. So if this term here vanishes, and the vanishing of this term is a condition on the initial state. If the initial state of the system is such that this term vanishes for all times within some time interval, then at least during that time interval, the behavior of the system depends only, at a given time, depends only on the relevant part at that time in earlier times. So insofar as we can choose boundary conditions for the system such that the middle term vanishes for all times within a time interval we care about, then we've actually separated off the irrelevant and relevant dynamics. We've got dynamics for the relevant part only. And what a necessary condition would be for that term vanishing is kind of a bit fiddly, but notice there's one dead easy sufficient condition, just set the irrelevant term to 0. Remember, these are linear operations. So if the state was initially in the representative space of states at the beginning time, this term vanishes for all subsequent times. So a sufficient, although by no means necessary...
You mean if it was initially the representative state?
If it was initially any representative state.
Yeah. One of the representatives.
Yeah, that's right. If it was initially one of the representative states, then I have a decoupling for all time, in fact, of that dynamics from what the irrelevant ones do after that.
Sure.
I mean, formal decoupling, because something's being trapped indirectly by some of the dynamics. But as I say, one can envisage much weaker criteria. In fact, one can show there must be much weaker criteria for it to vanish than just the term itself vanishes. But that at least will do it, yeah.
So you said these are, so the x's now are probability distributions. So
Well, abstractly, they're states in linear state space. But in classical physics, probability distributions are the paradigm example. In quantum physics, mixed states would be. This technology won't work for pure states in general.
So you get rid of the second term by the technique you described. If you take a second time derivative, is there some way to reduce that down to a soluble, a deterministic equation? You need a boundary condition still with velocity, as it were, to get the thing going. Or are we stuck with this differential integral?
My dynamics is first order, so my XR here is a state.
That's fine as it is, but when you've got something as complicated as that, where you've got a first order derivative on the, for time on the left, and then you've got an integral on the right.
Yeah.
I'm just thinking there's simpler ways of writing the same equation. So I'm thinking hit it with a derivative operator again, and then see that would turn the integral into.
Yeah, that's an interesting question. I don't immediately know. I'm going to come to that term in a slightly different way, but that's what happens if you just turn it to a second order equation. I'm not entirely sure. It's a nice question. Okay, so
why would it work for pure states? Just because.
Well, okay. Let me rephrase. I don't know for sure if it wouldn't, in principle, work for pure states. The projection maps that get used in applications in quantum mechanics don't. They tend to be projections on the mixed state space rather than on the pure state space. I don't know an application where that's not the case. It's an interesting question, actually. I don't know for sure. My guess is that you just confine the system to a certain Hilbert space subspace. No, I mean, think about it this way. The properties I'm going to be interested in for a quantum mechanical system are generally going to be something like distribution of probabilities with respect to certain observables. If my projection map is a projection on the space of pure states, it's generally just going to lock me into a certain space of observables, so that's not going to work as a projection map of the kind I'm looking for. But that's off the top of my head. It's an interesting question. All right, so we have this nice feature that if that second term in this expression due in particular to Swansea turns out to vanish, I've got a decoupling. And then this term, notice this term's behaviour doesn't depend anything on initial conditions. So the kernel of this thing doesn't depend on initial conditions. I can study it as a dynamical object. Suppose one can motivate or show that this object Z3 of Tor here changes over time very rapidly compared to the rate of change over time of the representative part of the state. Now, if that's true, two nice things happen. First nice thing that happens is that this integral, which I've taken to time little t, I can take to some very large value, because this thing will have dropped off close to zero long before I get into the vicinity of this time t. So if you imagine, suppose I've got, this is an operator, I should say, not a real number, so this is a slightly schematic way of representing it, but to get the idea, if I've got Z3 of tau has that kind of form, or is even more sharply peaked than that, if it has that kind of form, then the fact that I cut the integral off at t rather than letting it go up to some really, really large value doesn't matter. Depending how you idealize, you could take to infinity. In finite systems, Poincare recurrence, at least for quantum mechanical systems, tells you that it'll eventually come back up and be big again, but we can choose some really, really large time t and other thing. So if that's the case, this term I can approximate, on that assumption, this term I can approximate, go from little t to some fixed value, big T. And secondly, this term varies very, very rapidly with respect relative to the timescales in which this thing evolves. So I can approximate this thing as constant in doing the integral. So under those approximations, I get the original expression get that out. And that is just a linear operation acting on the representative part of the state. So under the two assumptions that one, the irrelevant, this second term vanishes, either because I've just set the irrelevant part to 0 at initial time, or for more complicated reasons.
But let me just, setting the irrelevant part to 0 at the initial time is just choosing an initial distribution that's non-zero only at the representative point. Is that right?
No, careful, the representative point is a representative distribution.
I'm sorry, is it right. Oh, right, sorry.
It's a point in the state space, and the state space is a space of distributions.
Sorry.
Yeah.
Good.
So.
Oh wait, but now, so. I see. A representative distribution, by analogy with what we were earlier calling a representative point, is the one that gives us a reduced dynamics. How are we defining a representative distribution?
At this stage, formally, it's the I've got my reduction map. My representative distribution is chosen as one of the points in the pre-image of any given point of the reduction map.
But that we can do. Maps like that always are available. Is there a further constraint that this map leads to a reduced dynamics?
Well, no, I haven't made that assumption at all yet. But I bet it better obey certain things if the thing I'm setting up is going to have the kind of properties I'm interested in.
Okay.
So just to reiterate that package of stuff we've got on the table, this term is just reversible, well-behaved dynamics. This term can be set, whether this term vanishes or not, is a boundary condition on the initial state. We know in closed form some states that satisfy it, the ones where the initial state is a representative state. There's no reason that there could well be others. But in any case, eliminating this term is a matter of the initial condition of the system. This term, under certain assumptions about the dynamics, which are not in any way dependent on the initial state, this term, under those assumptions, becomes a differential operator in the state at time t, a linear operator in the state at time t. So under those two separate sets of assumptions, one about the initial conditions and one about the dynamics, this equation, for the periods of time that these assumptions are valid, this equation becomes a straightforward differential equation in the state, and that's a reduced dynamics, because that's a closed form dynamic for the state. Yeah.
I'm sorry. I'm just being dense here. I'm trying to hook this up with the earlier discussion that wasn't about probability distributions.
Yeah.
Here, J, are there any restrictions on what kind of mapping? J is just some mapping that establishes equivalence classes among distributions.
Yeah.
That is, J is some mapping that you consider the whole space of distributions.
Yeah.
J divides it up into chunks by mapping certain sets of distributions onto a representative one for them.
Yeah. And
there are no further requirements as yet on what J is.
It's linear, but other than that.
Okay. And where is the dynamics coming from?
The dynamics is stipulated, but the fact that I get a reduced dynamics relies on this term being
so the dynamics so there's some fundamental stipulated dynamics on the distributions.
That's right.
Not on the individual states that their distributions over.
I'm not actually the fact that I'm interpreting these things as distributions is just interpretive gloss to help you think about them.
Good.
I'm not actually making any formal use of the system other than it's just a linear state space.
And the claim is that for any dynamics of that form, the equation below will hold.
Yeah, this is an exact result for
okay, good.
Wayne, then you'll see.
Okay, so that will always hold, but for in order to be useful, certain things have to happen.
Exactly.
Like you want something that starts out in the irrelevant part to remain irrelevant for a long time, right? And that's a non-trivial assumption.
Yeah, I'm not quite sure that's an accurate gloss of what that state, of what the vanishing of this means, but yes, within that constraint, yeah.
All right, okay. And then you want this third term to satisfy something like
that's right,
that.
yeah. So the vanishing of this, for this equation to reduce to a proper differential time-local, basically time-local equation for the relevant part, that is, for this to give me reduced dynamics, under whatever assumptions, I need two things to happen. Firstly, this term, which couples the relevant part, the irrelevant term has to vanish. And secondly, this term, which is integro-differential and time-dependent, needs to be approximable as an ordinary linear operation on x r of t. Now, just to finish a second. So what I think is interesting about the way of framing out, part of the way I push through this is the foundational point of view, and why I'm sort of the word labouring through some slightly hairy maths, is that it gives a certain amount of meat on the bone of that heuristic way, because it gives us rather sharply mathematical conditions that need to be satisfied. I think probably not mathematical conditions at the level of full-dress mathematical rigour, but fairly sharply understandable mathematical conditions for what kind of things we need to assume about the initial state and the dynamics, and assumptions which, at least on one way of reading them, separate out what we need to assume about the initial state from what we need to assume about the dynamics. So, for instance, although I don't think this application runs much in practice, we take John's example of coarse graining, where we replace the distribution with a certain smoothing of that distribution. If we think about that from this version, then the vanishing of this second term requires that the initial distribution is smooth in just that way. And the vanishing, or rather, a sufficient condition for the vanishing of the second term is that the distribution is smooth in just that way. And the vanishing of the third term doesn't depend at all on the initial distribution, but does depend on whether the dynamics have the right kind of relative insensitivity. And I should say what you normally do in application of this formalism is that you expand it in perturbation theory and look at the perturbative terms. Yeah.
You describe the second condition as a constraint on the starting state. Presumably one could equally think of it as a constraint on J. When you starting state, you can choose a J such that the starting state is one representative.
Yes, I hedge slightly because it's only a constraint. It's a constraint on the starting state only in the sense that I can kill it just by setting this thing to 0 independent of J. So there's no the condition. A sufficient condition for this to vanish is that the irrelevant part is 0. That's independent of what the dynamics are, although of course not independent of J.
For any starting configuration, you could choose a J that took that starting configuration as one of the representative points.
I don't know if that's true. Remember, this has got to vanish for all time, so this is an infinite set of conditions.
I see. Okay.
So you'd have to. I mean, this unlovely thing is the formal shape of the equation. So you'd have to invert. You'd have to look at this framework. You have to solve that killing things for all t. That's actually quite a strong constraint.
But XR0 is the irrelevant part of the starting state, right?
Yeah. So that's not time dependent, but this term in the expression is time dependent.
But it's linear, isn't it? So if XR0 is 0, that whole term.
Yeah, so that always works. By setting, that's the point. But one way to impose the vanishing of this term is a pure initial condition state. Just declare that the initial state is a representative state.
I think it's the idea that we...
No, I think we'll say the same thing. For any given starting state, you could always contrive some map.
Oh, I'm sorry, I see what you mean. You're saying just pick, yes, that's correct, but...
you push the bump of the cart onto third condition, presumably, a certain starting configuration.
Yeah, I mean, also, bear in mind that this comes to Joss's legitimate worry, not as if we have an algorithmic way of thinking of J's, it's a certain amount of try and see. The kind of routes we have to these things tend to be driven by wanting something that looks at certain low frequency details. So fine dependence on initial state is not normally the kind of thing you want to be looking at.
So once you pick your J, it's then straight to the starting state.
Yeah. And remember also that we're looking for dynamics here. So what we don't want is something which has a kind of sensitive functional dependence between what we write down as dynamics and what we write down as initial states. I mean, ideally the way dynamics works, you just have one dynamical rule and the initial state doesn't matter. Now, statistical mechanics is already requiring us to kind of welch a little bit on that ideal, but we don't want to go too far in that direction. Okay, I think we're at 6. That more or less got to the end of what I wanted to cover, I think. I'll have to keep you any questions. Yeah, when?
If we want to learn more about this framework, is there a good reference where this is spelled out nice and neatly?
Kind of. I mean, I originally came across it in Data Z's physical basis and direction of time, although it's not, I think its importance is not overstressed in that framework. I actually then went back to Zwanzig's original papers in the 70s, which I think are referenced in Zay. I mean, they're not particularly easygoing, but he's a good writer, he's clear, but he's fairly engaged in the calculational details, so you have to go.
Better than Big Machine.
Yeah, well, I think actually, I mean, I don't know the history of this stuff terribly well, but I think some of this kind of formalism came out of Zwanzig taking kind of ideas that were kind of tacit and implicit in some of the Prigogine group and doing something a lot kind of cleaner and tighter with. There were various really nice review things in the early 70s about it. I'm trying to write something up about it, but I don't have it at the moment.
There was this guy in Cambridge long ago, 20 years ago, who worked in Red Hat's group, who wrote a very good article on Prigogine subdynamics. I can't think of his name now.
I know the one you
But
mean.
he was one of the colleagues of Rob Clifton at that time.
Yeah.
He was Greek, right?
I know the paper, but I can't place the name of it.
So I'm not sure, you might have already touched on this a little, and we're probably going to discuss this in more detail, but I'm just wondering, you kept saying like we could set the irrelevant part just by fiat to being zero. Would there be any sort of justification we could have instead of just claiming it?
Okay, so let's kind of back off and do a kind of view from infinity here. We like to get, and I've been looking, a lot of the thing what I was doing was trying to get a bit close to some of the details and all. But here's the kind of bird's eye view, if you like. We have irreversible behaviour going on in the maths. We have a dynamics which, depending a macrodynamics which, depending how you look at it, either violates time reversal invariance or at the very least time translation invariance by having a deferred starting time. We have an underlying microdynamics which is time translation and time reversal invariant. As a matter of logic, we can't get from the one to the other without adding an additional ingredient of some kind. The two initial, as long as one's continuing to think in terms of think of this in terms of dynamics and not in terms of sort of external agents or engagements of that kind, basically the two spaces you have available to break the symmetry is either by some condition on the state, normally on the initial state, or some condition on the dynamics. In other words, welch on your original promise that the underlying dynamics were time reversal invariant. If you go the first route there, then the question of what the justification is for the initial condition is going to be a philosophical question, and people have gone in rather different directions there. I mean, one thing you could say is, well, look, it's by its fruits shall ye know it. Making a posit of that kind is powerfully explanatory for various purposes. I mean, the posit here is what I think this brings out is something I kind of argued for in rather more qualitative ways in other places, that if you look at the structural dynamics, the kind of condition you seem to need to get the irreversibility out as a microstate, as an initial state condition, just in terms of these equations, not in terms of necessarily the grand scheme of it, looks less like a condition on the macro details, such as, say, the bulk entropy of the system, and more a condition on the micro details within that. I mean, if you were to map it onto some of the literature on the past hypothesis and Boltzmannian approaches that's been discussed at various points in the literature post, particularly David's book, but I mean, lots of places, then this kind of condition is actually something you want to think about as something like the smoothness of the probability distribution over the initial state. It's silent on what the initial macro state is. Insofar as we need initial macro state conditions, we need them for some other reason than to underpin this kind of analysis.
Just very quickly, so if this does break time translation variance, is that going to lead to violations of conservation of energy, or any problems regarding that?
No, you're worried about narrative type routes. I have to say I hadn't quite thought about it. I mean, the equation is just an approximation. The result given here is just an approximation scheme to to derive an equation for the underlying, for some feature of the dynamics of something which at the underlying level is still carrying on perfectly happily. So at some sufficiently deep level, no, it can't do that. Whether there's something that looks like it in the approximative regime, I don't know. The equations you tend to get out of these schemes, sometimes they don't. Sometimes they have a tendency to bleed energy into the irrelevant degrees of freedom. So an application of this kind of technology would be to something like fluctuation dissipation results. So if I have one example of using this kind of machinery, if I have a large particle in a bath of smaller particles, so my projection might well be that I replace the bath of smaller particles with just a kind of its uniform state or something, and keep track of the degrees of freedom of the particle. And what you get out of that kind of equation is fairly standard kind of Brownian motion type stories, which have a fluctuation term, but normally also a dissipation term. So you don't have conservation of energy within the equation you get out, but you've got a physical understanding of what's going on because you're bleeding energy into the medium. Other cases, what you'll get out is equations where the expected value of the energy is being conserved, but the actual spread of energy across the spectrum isn't being conserved. And again, the way you want to think about that is certain correlations between the relevant and irrelevant degrees of freedom are being averaged over, so that if you imagine I've got system A and system B are correlated, and I have an energy conserving interaction between them, so you can easily see situations where just tracing over the second system would smear the first system's energies out. I mean, in a sense, there's an overlap here with some of the ways in equilibrium statistical mechanics you think about systems in thermal contact with heat baths. So if I take a really big system which has a definite energy, and I look at its equilibrium state, so it's uniformly distributed across a definite energy surface, but the state of of each of the systems separately has a lot of energy spread. That's compatible with the total system energy being an eigenstate of energy, definite energy classically, because there's a correlation between energies such that if the first system has a higher energy, the second system has a lower energy. If you trace over the second system, if yours once in projection just means throw away the second system and look at the marginal of the first system, then you're going to have a violation of conservation of energy at the fine grain, even if the expected energy is fixed.
The name I was thinking of is Karakostas.
What's the name again?
Karakostas. And he wrote in Philosophy of Science in 1996 on the Brussels School's error of time in quantum theory.
And the nearest
another paper I found very helpful was Opsimea and Brandes, analysis of Ricochet's theory of subdynamics in Annals of Physics, 1983. Don't know if you like that.
I don't know these. I mean, I looked at the thing with Karakostas work, but I had to say I didn't get deeply into them. Insofar as I can understand them, they're kind of very obscure, to be honest. Then I think a lot of the formal machinery was being used in similar ways, but it was being run from quite a different interpretive move. It was almost meant to be identifying the bit that was going to be a modification of the dynamics in some way.
Yeah. That was Panzig's important realizations, and that the machinery in different interpretations was actually mathematically identical.
Yeah.
Thanks, David.